The water is warm, and it is very dark, and somewhere below you a long shape is moving without any hurry at all. You cannot see all of it. You can only feel the slow displacement of water as something turns far beneath the surface, the way a current shifts when a large body passes through it, patient and unbothered, on its way to somewhere it has been before. It is dusk over a sea that no longer exists. The light is the colour of weak tea, gold thinning into grey, lying flat across water that stretches in every direction until it meets a low and distant shore. There is no land beneath you for many miles. There is only this shallow warm sea resting across the middle of a continent that will one day be split into states and provinces and wheat fields, though none of that has happened yet, and none of it will happen for a very long time. The shape rises. Slowly, without breaking the calm, a small head lifts clear of the surface at the end of a neck longer than anything you have a name for. The head is no larger than a horse's. The neck behind it is the length of a fishing boat. It draws a single breath, an unhurried sound, more sigh than gasp, and the water beads and runs from smooth dark skin, and the eye that turns toward the fading light holds nothing urgent in it at all. This is an Elasmosaurus, and the breath it has just taken is one of perhaps 100,000 it will draw this year, and the place it is resting now is roughly halfway along a journey of nearly 10,000 miles. That is about 16,000 kilometres. It is a distance greater than any land animal of its age will ever travel, and the animal making it is not built for speed or for endurance in any way that looks like effort. It is built for patience. It is built for the long, slow following of warm water across a sea that wraps itself round the heart of a continent. You have probably heard of the great hunters of these waters, the mosasaurs, the giant sharks, the predators with names that sound like weather. This is not their story. This is the story of the long-necked traveller that moved among them, quietly, for the whole of its life, following the warmth north in the spring and south again in the autumn, crossing distances we are only now beginning to measure by reading the chemistry locked inside its bones tens of millions of years after the last of them drew breath. It is a migration almost no one talks about. It left no footprints, because it happened in open water. It left no obvious trail, because the sea that carried it has been gone for 66 million years. And yet the evidence is there, written in the growth rings of fossil bone and in the faint chemical signatures of waters this animal swam through long ago, waiting patiently in stone for someone to learn how to read it. Tonight, we are going to follow that journey from beginning to end, slowly, in no hurry at all, the way the animal itself once did. So let the day you have just finished settle behind you. Let your breathing slow to match the rhythm of the water. There is nothing here that needs your attention, nothing that asks anything of you. There is only a warm and ancient sea, and a long dark shape resting in it as the light fades, and a journey that has already happened. Safely, completely, a very long time ago. You're simply here to watch it unfold. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly. Let yourself sink a little deeper now, into the cushions, into the warmth, into the quiet. The sea is waiting, and it is in no hurry, and neither are we. We will begin where the journey begins, in the shallow southern reaches of a vanished ocean, where the water is warmest and the light lingers longest, and where a long-necked animal is about to turn its small head north toward a summer it has crossed half a world to reach. Begin with a fact that geography has long since buried. Approximately 80 million years ago, there was no middle of North America. There was no Kansas, no Nebraska, no flat interior plains stretching between mountain ranges east and west. In their place lay open water, a shallow, warm, enormously productive inland sea that reached from what is now the Gulf of Mexico all the way north to the Arctic Ocean, cutting the continent cleanly in half for millions of years. Geologists call it the Western Interior Seaway. You can think of it as the sea that swallowed a continent from the inside. It was not a narrow channel. At its widest, during the peak of its existence, it stretched to roughly 900 miles across, which is about 1,400 kilometres. It was shallow by the standards of modern oceans, most of it no deeper than about 2,000 feet or 600 metres, and much of it considerably shallower than that. In the southern reaches, where the sea spread across what is now Texas and New Mexico, The bottom lay within the reach of summer sunlight for much of the year. In those places the seafloor was bright, alive and restless with the movement of creatures feeding close to the sand. What made the seaway possible was not any single dramatic event, but a slow accumulation of conditions that took tens of millions of years to assemble. The global climate during the late Cretaceous period was dramatically warmer than today, warmer in ways that are difficult to hold in the mind without some effort. There were no polar ice caps. There was no permanent ice anywhere on the planet. Sea levels stood perhaps 200 meters higher than they do today, and that difference was not merely a matter of a few flooded coastal cities. It was the difference between a world with interior land masses and a world where those interiors quietly became seafloor. The water temperatures along much of the seaway's length were closer to those of a modern tropical lagoon than to the cold grey seas most people associate with North America. Isotopic analysis of fossilized shells, a technique that reads the chemistry of oxygen atoms preserved in calcium carbonate, the way tree rings preserve a record of wet years and dry ones, has allowed paleontologists to reconstruct surface water temperatures with reasonable confidence. In the southern reaches of the seaway, water temperatures likely approach 30 degrees Celsius, or about 86 degrees Fahrenheit, during the warmest months. Even in the northern reaches, near what is now Alberta and Saskatchewan, the water rarely dropped below the temperatures you might find in a warm Mediterranean summer today. Warmth is not merely a comfort. For marine ecosystems, warmth is the engine that drives productivity. The warm, shallow waters of the Western Interior Seaway were extraordinarily rich in nutrients, circulated constantly by tidal forces and seasonal temperature gradients moving water from the Arctic end of the seaway southward and back again. Blooms of microscopic plankton provided the base of a food web that supported everything from palm-sized ammonites to animals nearly 60 feet long. The seaway was not a quiet backwater. It was one of the most biologically productive marine environments the planet had ever produced. And there is something about it that is very easy to overlook, something that matters enormously when you're trying to understand the migration we have come here to follow. The seaway was connected at both ends. In the south, it opened into the warm waters of what geologists call the Tethys Sea, an ancient tropical ocean that no longer exists as a distinct body of water, but that formed the warm central band of the Cretaceous world. In the north, it opened toward Arctic waters that, warmer than today's polar seas, were nonetheless cooler and seasonally variable. The seaway was therefore not an enclosed lake. It was a passage, a long connected two-ended corridor through the middle of a continent, with warmth at one end and cold at the other, and every temperature in between along its length. This geometry matters. It is the architecture that made migration possible. An animal that needed warmth to feed, that was warm-blooded enough to function across a range of water temperatures, and that was large enough to cover distances that would be meaningless to a smaller creature could, in principle, follow the seasonal gradient of this corridor from end to end. The question is whether any animal actually did. The answer, written not in footprints but in the chemical memory of fossilized bone, is yes. And the animal that did it was not the most famous predator of these waters, not the mosasaur or the great Cretaceous shark. It was the long-necked traveller that moved through these seas with the patience of something that understood, at a biological level below the reach of thought, that the warmth would always return if you followed it far enough. Picture the seaway now as it would have looked from above. Imagine the perspective of one of the large pterosaurs that crossed these waters regularly, a wide, still expanse of blue-green water stretching to the horizon in both directions. The shores are distant and low, lined with subtropical vegetation that has pushed as far north as conditions permit. In the water itself, visible from above as movement rather than shape, various forms of life are going about their business in the ordinary way of creatures that have never known any other world. Schools of fish move through the upper water column in loose, shifting formations. Ammonites, squid-like animals with coiled shells, some no larger than a coin and some nearly 2 feet across, drift in the middle depths in numbers that are difficult to imagine from the perspective of a modern ocean. Deeper down, mosasaurs are moving. You can trace their path by the way the fish schools scatter and reform behind them, and somewhere in the mix, not chasing anything, not being chased by anything at this particular moment, a long neck is tracing a slow, unhurried arc through the water as the animal attached to it rolls and turns and resettles into a new position, as if adjusting itself to the quality of the light. The sediment at the bottom of this sea, accumulating layer by layer across millions of years, would eventually become some of the most famous fossil-bearing rock in North America. The Niobrara Formation, which today forms distinctive chalk bluffs in Kansas and Nebraska, was laid down entirely within this seaway. So was the Pierre Shale, which extends across much of the northern Great Plains from Kansas northward through the Dakotas and into Canada. These formations represent millions of years of slow accumulation, the shells of plankton, the bones of fish, the occasional larger animal that sank to the bottom and was preserved in the fine-grained sediment settling around it. What is remarkable about these formations is not merely their age but their completeness. The Niobrara and Pierre Shale have produced an almost continuous record of life in the Western Interior Seaway across tens of millions of years. Paleontologists working these formations for well over a century have recovered mosasaurs and plesiosaurs in numbers sufficient to reconstruct entire ecological communities. They have found sharks and giant fish. They have found birds and pterosaurs that lived at the water's edge or fed directly from its surface. And they have found, in numbers that would not surprise anyone who understood the seaway's productivity, specimen after specimen of the animal we have come here to follow. The Western Interior Seaway was not, it should be understood, a permanent feature of the landscape. It came and went across a very long interval of geological time, controlled by the slow dance of tectonic forces raising and lowering the seafloor, by the global temperature that determined how much water was locked in polar ice versus circulating through the oceans, and by factors more complicated than either of those. In its earliest form, the seaway began assembling perhaps 100 million years ago, as rising sea levels from a warming climate began flooding the low interior of the continent from both the north and the south simultaneously. The two arms of the flooding sea connected somewhere around what is now Kansas, approximately 95 million years ago, creating the full north to south corridor for the first time. For the next roughly 30 million years, an interval of time so large it makes all of human civilization seem like an afternoon, the seaway persisted, deepening and shallowing with changing conditions, retreating to the north and south as sea levels fell, expanding again as they rose. The animals that lived in it evolved alongside its changing geography, and the migrations that some of them undertook were shaped by the seasonal and geological rhythms of the corridor itself. Toward the end of the Cretaceous, as the Rocky Mountains began their slow rise and the tectonic plate underlying the western part of the continent began to lift, the seaway began to shallow and ultimately drain away. The process took millions of years. It was not a catastrophe in any meaningful sense. A creature living through the final retreat of the seaway would have noticed nothing unusual in the course of its own lifetime. But over the long scope of geological time, the water withdrew, the land reasserted itself, and what had been a rich and ancient sea became the dry interior of a continent, its former existence preserved only in the chemistry of the chalk and shale left behind. It is in that chalk and shale that the bones of our traveller rest, and it is in those bones, not in the gross anatomy that tells you what the animal looked like, but in the microscopic chemistry of the material the bones are made of, that the story of the migration is written, waiting for someone to ask the right question and apply the right technique. We will come to that in time. For now, settle into the knowledge that the sea existed, warm and wide and improbably rich, cutting through the middle of a continent that has long since reclaimed its interior. The animal that crossed it twice a year, for the whole of its long life, is resting just below the surface of the warm southern water as we begin. Its breath has just broken the stillness. It is time to introduce it properly. There is a moment, early in the study of any extinct animal, when the bones stop being a collection of parts and begin to tell you something about what it was like to be the creature they belong to. The Elasmosaurus arrives at that moment quite suddenly, and it arrives in a way that makes most people pause, because the first thing you notice looking at a reconstructed skeleton, or at the diagrams that paleontologists have assembled from specimens recovered across the Great Plains, is the neck. The neck is longer than everything else. The neck is, almost improbably, the main event. Elasmosaurus platyurus, the species that gives the whole group its name, carried 72 cervical vertebrae, that is 72 neck bones. For comparison, a giraffe has 7, a blue whale has 7. Every mammal alive today, from the smallest shrew to the largest elephant, has 7 neck vertebrae, a number that appears to be so deeply embedded in mammalian biology that not even the extraordinary evolutionary pressures shaping whales or bats managed to change it. Elasmosaurus had more than 10 times that number, linked in a chain that produced a neck stretching to roughly 14 feet in length, which is about 4¼ meters. The total body length of a full-grown elasmosaur varied across species, but the larger individuals reached approximately 40 to 46 feet, which is about 12 to 14 meters. Of that total, perhaps half to slightly more was neck. The animal's body, the barrel-shaped torso containing the organs, the 4 paddle-shaped limbs, the relatively short and tapering tail, occupied what remained. Imagine, if you will, an animal roughly the length of a city bus, with a neck as long as half that bus attached to one end, tipped with a head not much larger than a sheep's. This was not an animal that announced itself dramatically. It was an animal shaped by a very specific kind of patience. The head is important. It stayed small even as the rest of the animal grew to impressive dimensions, and this is not an accident of proportion, but a functional requirement. A large, heavy head at the end of a 14-foot neck would have created mechanical problems of extraordinary complexity. The muscles required to hold it up and move it with any precision would have dominated the animal's energy budget. Instead, the head remained light and narrow, with jaws lined with long, slender, interlocking teeth that point slightly outward from the jawline. These teeth are not crushing teeth. They are not designed for anything that requires sustained force. They are designed for a single, specific task, closing around a slippery fish before it can escape. Picture those teeth for a moment. They are thin, sharp, curved very slightly inward, and when the jaws close they interlock like the tines of 2 forks pressed together. A fish caught between them has nowhere to go. The prey cannot push sideways and slip out, the way it might escape from a predator with a wider, more open jaw arrangement. The interlocking design holds whatever enters it with remarkable efficiency, even as the head moves and the neck repositions and the Elasmosaurus settles its catch into a position suitable for swallowing. It is the dental architecture of something that has to be right on the first attempt, because a second attempt at a fish that has already been alarmed is considerably harder than a first attempt at a fish that has not yet registered the presence of the animal approaching it. The 4 limbs deserve attention as well. They are not fins in the sense of flat, rigid appendages. They are paddles, broad, flat, flexible structures built from elongated finger bones covered in connective tissue, shaped somewhat like the blades of oars but capable of more complex movement than any oar has ever managed. Plesiosaurs, the broader group to which elasmosaurs belong, were not tail-propelled swimmers the way fish and most other aquatic vertebrates are. They were wing-propelled swimmers, using a flight-like motion of their front paddles and a complementary motion of the rear paddles to generate both forward thrust and precise maneuvering control. Researchers who have modelled this locomotion using computer simulations describe it as something between underwater flying and rowing, and the comparison is apt in the sense that it suggests a fundamentally different relationship between the animal and the water than the side-to-side body undulation used by fish and mosasaurs. This method of locomotion is slower, on average, than tail-based propulsion. Elasmosaurs were not built for the explosive bursts of speed that a mosasaur could generate, or for the sustained high-velocity cruising that the larger sharks of their era were capable of. Estimates suggest they move through open water at perhaps 2 to 4 miles per hour under ordinary cruise conditions, with the capacity for somewhat faster burst when circumstances required. 2 to 4 miles per hour is a human walking pace. It is not an impressive speed for an animal navigating 10,000 miles of open sea. And yet it is entirely sufficient if you are patient. Migration is not about speed. Migration is about consistency, about the ability to move in the right direction at a pace that is sustainable across weeks or months, maintaining that pace through changing conditions, through cold patches and warm patches, through scarcity and through abundance. A grey whale, one of the longest distance migrants in the modern ocean, travels at an average speed of approximately 3 to 5 miles per hour during its migrations between breeding grounds in warm waters and feeding grounds in cold ones. It takes the grey whale roughly 2 to 3 months to complete a one-way journey of about 6,000 miles. Elasmosaurs, covering 10,000 miles at comparable speeds, would require a journey of perhaps 3 to 4 months, one way. The arithmetic is demanding but not impossible. for an animal whose entire biology was organised around the long, patient following of warmth. Here is one of the facts about elasmosaurs that doesn't appear in most documentaries because it is recent and somewhat uncertain, but it is worth knowing. Some researchers studying the gastroliths found in elasmosaur stomach cavities, gastroliths being smooth stones that many prehistoric reptiles swallowed, long thought to function purely as digestive grinding aids, have proposed a second possible function for these stones. The idea is that the gastroliths might have served, at least in part, as ballast. Ballast in the same sense that a diver uses a weight belt, to fine-tune buoyancy, to maintain a stable position in the water column without constant muscular effort. If this interpretation is correct, it suggests that elasmosaurs were capable of holding a particular depth with very little expenditure of energy, simply resting at a chosen position in the water and allowing the weight of the stomach stones to hold them there while they waited. Waiting, as we will see, was central to how they hunted. It may also have been central to how they travelled. The skin of elasmosaurs is known from very few specimens, because soft tissue preservation is extraordinarily rare in the fossil record, particularly for large marine animals whose carcasses typically decomposed or were scavenged before burial. But from what evidence exists, impressions in fine-grained sediment, chemical traces in well-preserved specimens, the picture that emerges is of a smooth-skinned animal without external scales in the heavily keeled sense that a crocodile, for example, possesses them. The skin was likely close-fitting, streamlined, similar in texture and general appearance to the skin of a modern sea turtle or a large ocean-going cetacean. Dark on the dorsal surface, likely lighter on the ventral side, a counter-shading pattern common in open-water animals that provides some degree of camouflage both from above and from below. The eyes were large relative to the head. This is consistent with what is known about the visual requirements of animals hunting fish in open water, where depth perception and the ability to track fast-moving prey against a complex background of moving water and variable light is more important than binocular field of view. Large eyes gather more light, which is useful in the lower reaches of the water column, where a long-necked animal hunting upward from below might spend much of its time. The nostrils were positioned toward the front of the skull, and the nasal passages connected internally to the palate, in a way that is consistent with an air-breathing animal that surfaces regularly but spends the great majority of its time submerged. Reproduction in elasmosaurs remains partially uncertain, but the evidence that has accumulated over the past several decades leans strongly toward live birth rather than egg-laying on beaches. No nesting site associated with a large plesiosaur has ever been confirmed. No eggshell material has been associated with elasmosaur remains in a way that survives scrutiny. And crucially, at least one specimen, a partial skeleton recovered from Kansas and described in research published in 2011, preserved within the abdominal cavity the remains of what appears to be a single, large embryo, roughly 1/4 to 1/5 the length of the adult. The size of that embryo, relative to the adult, suggests that elasmosaurs gave birth to one offspring at a time, and that the offspring was large and relatively capable at birth. This reproductive pattern has implications for how we think about the migration. A single large offspring, born capable and immediately independent in open water, required no return to a beach, no nesting behaviour, no seasonal adjustment of the migration route to accommodate the vulnerability of newly hatched young. It could enter the sea at whatever point in the annual cycle its mother happened to be occupying, and if it was large enough and capable enough to follow the migration from its first weeks of life, then the migration itself was not disrupted by reproduction. The journey continued. It always continued. That is perhaps the deepest thing the body of an elasmosaur tells you when you look at it long enough. Everything about it is built for continuation, not for speed, not for dramatic effort, but for the slow, patient, uninterrupted act of going forward. The length of an elasmosaur's life is not known precisely. No method yet developed can read a death date from a fossil, but growth ring analysis of fossil bone, examining the annual growth bands laid down in cortical bone the way tree rings record annual growth, and counting them the way you would count rings in a cross-section of timber, suggests that larger individuals took at least 2 to 3 decades to reach full size, and that some individuals may have continued growing slowly for considerably longer. Lifespans comparable to those of large modern sea turtles, 60, 70, perhaps even 100 years, are plausible, though unprovable. If that is the case, then a single elasmosaur might have completed this migration 50 or 60 or more times in its life. 10,000 miles a year, twice a year, for half a century or more. It becomes, when you hold that number in your mind, something larger than a simple biological behaviour. It becomes the defining rhythm of an entire existence. The warmth in the south as winter ended, the long move north, the Arctic summer with its continuous light and extraordinary abundance, the turn south again as the water cooled, the warm return, year after year after year, the same corridor, the same gradient of temperature, the same seasonal pulse of life, moving through the warm, shallow water of a sea that is now as much a memory as the animal that crossed it. Settle into that rhythm now, let it carry you. There is a long journey still ahead, and it begins, as all journeys begin, with the first movement forward. If you are drifting now, let yourself go. Subscribe so the next story is waiting when you return. Sleep well. There is a room in a university laboratory somewhere. There are actually several scattered across institutions in the United States and Canada, where a researcher sits very still in front of a microscope, looking at a thin section of fossil bone under polarized light. The bone is perhaps 80 million years old. It is no longer bone in any biological sense. Every organic molecule that was once part of it has been replaced by mineral, by the slow infiltration of silica or calcium carbonate from the surrounding sediment over the course of geological time. What remains is a ghost of the original structure, a perfect mineral replica of a material that has not been truly alive for nearly the entire span of time since the last dinosaur breathed. And yet the information preserved in that mineral replica is extraordinary, if you know what you're looking for. The technique that has most transformed our understanding of where elasmosaurs went during their lifetimes is called isotopic analysis. It is a form of chemical forensics, a way of reading the environment an animal inhabited by examining the chemical signatures preserved in the mineral that replaced its original bone and tooth material. It works because of a property of water that might initially seem too small a detail to matter across geological time, but that turns out to be preserved with remarkable fidelity in the right conditions. Water is made of hydrogen and oxygen. Most of the oxygen in seawater exists in a common form called oxygen-16, meaning it has 8 protons and 8 neutrons in its nucleus, but a small fraction of the oxygen in any body of water exists in a heavier form called oxygen-18, which has 8 protons and 10 neutrons. The ratio between these two forms, the amount of oxygen-18 relative to oxygen-16, varies depending on where the water has been and what temperature it is at. Cold water has slightly more oxygen-18 relative to oxygen-16 than warm water does. Water evaporated and precipitated repeatedly through cloud systems tends to lose oxygen-18 preferentially, so fresh water arriving from rain and rivers tends to have a lower oxygen-18 ratio than open ocean salt water. Arctic water has a different ratio from tropical water. Water at the surface of the sea has a different ratio from water at depth. When a tooth or a bone grows, it incorporates the oxygen from the water around the animal, or, for air breathers like elasmosaurs, from the water they swallowed and processed metabolically, into its mineral structure. The ratio of oxygen-18 to oxygen-16 that ends up locked into the forming enamel or bone matrix reflects the ratio that was present in the water at the time of growth. This is a record that, under the right preservation conditions, survives for tens of millions of years with enough fidelity to read. What this means is that a single elasmosaur tooth is, if you look at it in the right way, a travel diary. The outermost layer of enamel, the last material deposited before the animal stopped using that tooth, reflects the water chemistry of wherever the animal was in the final weeks of that tooth's active period. The deeper layers, deposited earlier in the tooth's growth, reflect earlier waters, and because teeth grow in a particular sequence across an animal's lifetime, comparing the isotopic signatures in different teeth from the same individual can give you a rough sense of how that animal moved through environments with different water chemistry during its lifetime. The strontium isotope ratio preserved in bone offers a complementary record. Strontium, a metal element that behaves chemically somewhat like calcium, is incorporated into bone from the water and food an animal consumes. Different geological environments have different strontium isotope ratios, determined by the age and type of rock that the water has flowed over before being consumed. Marine water has a relatively consistent global strontium signature because the world's oceans mix thoroughly over geological time. Fresh water and brackish water, by contrast, carry signatures specific to the catchments they drain, which vary depending on the age of the underlying geology. An animal that moved between the open marine waters of the Seaway and the shallower, fresher river-influenced waters near the northern or southern shores would therefore carry a shifting strontium signature in its bone, with different layers reflecting different water chemistries. The challenge, of course, is that bone remodels throughout an animal's life. Old bone is replaced by new bone as cells continue working, so the strontium signature in a long bone is not a layer-by-layer diary in the same way that tooth enamel is. But in rapidly deposited bone material, in the annual growth rings visible in cross-sections of fossil long bones, the chemical signal can sometimes be read stratum by stratum, layer by layer, the way you would read the isotopic record in a stalagmite or a coral skeleton. The growth rings themselves are a source of information independent of chemistry. Bone in a seasonally variable environment often grows in pulses, depositing faster-growing, more porous tissue during periods of abundance and slower-growing, denser tissue during periods of scarcity or cold. The boundary between one year's fast growth and the next appears as a thin, dense line called a lines of arrested growth, or LAG, visible under polarized light as a dark band cutting across the bone's growth rings. Counting these lines gives you an estimate of the animal's age at death, and the thickness of the zones between lines tells you something about how good each successive year was for the animal in question. What do these techniques applied to actual Elasmosaur fossils tell us? The short answer is that they tell us these animals moved through a range of water chemistry conditions across individual lifetimes that would be consistent with seasonal migration across a geographically significant portion of the Seaway. Specimens from the Niobrara Formation in Kansas carry isotopic signatures consistent with the warm, more marine-influenced waters of the southern Seaway. Specimens from the Bearpaw Formation in Alberta and Montana, rocks deposited in the northern reaches of the same Seaway, where fresh water influence from northern river systems was more pronounced, carry somewhat different signatures. Whether these differences represent individuals that lived their entire lives at one end of the Seaway, or individuals that moved between both ends, has been a subject of active research for some years. The most compelling evidence for long-distance movement comes from individual specimens in which multiple teeth from different growth stages, or bone samples from different growth rings, carry isotopic signatures suggesting the animal inhabited significantly different water chemistries across its lifetime. These are not small variations, the kind that might result from an animal moving a few miles along a coastline between a river mouth and open water. They are shifts consistent with movement across a range of several hundred miles or more, from water with a strong marine signature to water with a stronger freshwater or brackish influence and back again. The pattern, for specimens in which it appears, is cyclical. It comes and goes in the record the way seasons come and go. It is worth pausing here to note how recent this line of inquiry is. The first detailed isotopic studies of plesiosaur teeth applying these principles to questions of migration were published only in the past 2 decades. The application of growth ring analysis to questions of plesiosaur physiology and migration behavior is even more recent. This is a field in which the fundamental questions are still being framed, in which the right specimens have in some cases not yet been analysed, and in which results published this year will be qualified or extended by results published next year. The picture presented here is the best current reconstruction, drawn from the available evidence, but it is a picture that continues to be painted. There is a deeper point here, one that goes beyond the specific question of Elasmosaur migration. The tools that have made this kind of inquiry possible, isotope mass spectrometry, micro-CT scanning of fossil bone, computer modelling of fluid dynamics around reconstructed skeletal geometries, did not exist for most of the history of paleontology. The scientists who first excavated Elasmosaur bones from the chalk bluffs of Kansas in the 1860s and 1870s were working with hammers and brushes and the unaided eye. They could tell you what the animal looked like. They could not begin to tell you where it went. The gap between what can be seen and what can be known is one of the recurring themes in the study of extinct life, and the tools developed to close that gap are perhaps the most quietly extraordinary achievements of modern science. A mass spectrometer analysing the oxygen isotope ratio in a fragment of Elasmosaur tooth enamel is in a very real sense reconstructing the temperature of water that an animal breathed through 80 million years ago. The fact that this is possible, that the record persists, that the signal is readable, that the instrument is sensitive enough, is not something that can be taken for granted. It is a genuinely remarkable capability, arrived at through decades of instrument development and applied with care and patience, by researchers whose names appear in footnotes to papers that most people will never read. Settle into that patience for a moment, the patience of the researcher in the laboratory, working carefully through a problem that cannot be rushed. The patience of the Elasmosaur, moving at walking pace through thousands of miles of warm sea. The patience of the stone itself, holding the chemical record intact across an interval of time that makes all of human history seem like an afterthought. These are different kinds of patience, but they share a quality that is worth noticing before we move on. They all belong to something that is not in a hurry, and that trusts the outcome will be worth the waiting. Here is another lesser-known fact that the rocks have quietly preserved, and that is worth carrying with you as we continue. The Niobrara Formation, the chalk formation in Kansas and Nebraska that represents the seafloor of the Western Interior Seaway at its peak, contains not just bones but the chemical record of the water column itself, preserved in the shells of microscopic organisms called foraminifera that lived at different depths and sank to the bottom when they died. By reading the oxygen isotope signatures in foraminifera shells from different layers of the formation, paleoceanographers have been able to reconstruct the temperature gradient of the seaway's water column across different seasons with considerable precision. The result is a map not just of the animal, but of the water it moved through, its temperatures, its chemistry, its seasonal character. The migration corridor, in other words, is not merely inferred from the bones of the animal that used it. It can be read from the sediment itself, layer by layer, season by season, across millions of years of accumulated record. The sea has told us where it was warm and when. The animal has told us, in the chemistry of its teeth, that it followed that warmth. What remains is to follow them both. It begins in the south, as most migrations do. The water here is as warm as it will be at any point in the year, shallow enough in places that the pale chalk sediment of the seafloor is visible through the surface when the angle of light is right. It is late winter by any seasonal reckoning, though the word winter requires some adjustment when applied to a world without polar ice. In the southern reaches of the Western Interior Seaway, the coolest temperatures of the year are still considerably warmer than a modern temperate summer. The seasonal swing is gentler than what people in the modern middle latitudes experience. But it is real. The water cools slightly, the days shorten slightly, the great seasonal bloom of plankton that drives the food web diminishes slightly. And then, in what corresponds to the late winter or early spring of the Cretaceous year, conditions begin to shift. The light changes first. It is the thing that animals sense before anything else. A quality of the light in the hours after dawn, the slightly longer arc the sun traces across the sky, the way the warmth in the water begins to feel less like something stored from the previous season and more like something new being added. You would not call the Southern Interior Seaway cold at any time of year, but you might call it in these weeks slightly less than entirely satisfying. You might feel a pull toward the north, toward water that will soon be warming faster than the water you currently occupy, toward the seasonal explosion of life that follows the advancing warm front northward, every spring like a wave. For an Elasmosaur in the southern part of the seaway, the response to this pull would not have been deliberate in any way we would recognize as decision-making. It would have been biological, built into the physiology and behavior of the animal over millions of years of natural selection, as automatic as the turning of a compass needle toward a magnetic pole. The water temperature around it, the changing light, the quality and abundance of the prey in its immediate vicinity, all of these would have combined into an internal state that caused the animal to begin moving north. Not urgently, not with the frantic energy of something fleeing, but steadily, persistently, at that characteristic 2 to 4 miles per hour, day after day and night after night, because the water it was moving toward was fractionally warmer than the water it was leaving, and fractionally warmer water held fractionally more prey. Here is a fact about the Western Interior Seaway that matters enormously for the migration's logic, and that most accounts of the seaway's ecology overlook. The seaway did not warm evenly from south to north in the spring. It warmed in a wave, beginning at the southern end where the water was already warmer, and the sun angle was highest, and progressing northward as the season advanced. The temperature gradient that an Elasmosaur moving north in spring would have encountered was therefore not a simple division between warm south and cool north. It was a moving front, advancing perhaps a few miles per day during the peak of the warming season, with warm and productive water ahead of it, and cooler, slightly less productive water behind it. An animal capable of moving at 2 to 4 miles per hour and sustaining that pace across days and weeks could, in principle, remain very close to this advancing warm front, staying in the zone of maximum productivity as it moved north, feeding heavily in the warm water just behind the advancing edge, never too far ahead into waters that had not yet warmed to full productivity, never so far behind that the front had passed and the productivity had already peaked and begun to decline. This is not a conscious strategy. It is simply what happens when an animal whose movement is driven by temperature and prey abundance moves in a direction where temperature and prey abundance are increasing. What did they eat, these travellers moving north through the Seaway's spring? The primary prey of elasmosaurs across their range appears to have been fish, small to medium-sized bony fish, the kinds that schooled in the upper water column and were accessible to an animal approaching from below with a long neck and a precisely engineered jaw designed for a single, accurate closing movement. The Seaway supported extraordinary fish diversity and abundance. The Niobrara Formation alone has produced dozens of fish species, ranging from small herring-like forms to the enormous Xiphactinus, the giant predatory fish that sometimes reach 20 feet in length. Elasmosaurs were not hunting the large predators. Their teeth and jaw design were not suited for anything much larger than a foot or two in length. But the small schooling fish were available in enormous numbers, and an animal moving north with the warming front would have encountered progressive blooms of them along the way. Belemnites, torpedo-shaped squid-like cephalopods related to the modern cuttlefish, were also abundant in the Seaway and appear frequently in the stomach region sediment associated with plesiosaur specimens worldwide. They were soft-bodied enough to be handled by the slender interlocking teeth of an elasmosaur, abundant enough to be a reliable seasonal resource, and they followed their own patterns of movement through the water column that might well have overlapped with the migration corridor. Ammonites, though shelled and therefore harder to process with the elasmosaur's fish-catching teeth, were nonetheless consumed on occasion. Their broken shells turn up in the abdominal region of some specimens, suggesting that at least some individuals found ways to manage the shells, either swallowing them whole in the case of smaller forms, or dealing with them in ways that the fossil record has not yet fully revealed. The experience of moving north through the Seaway in spring is not something any human has had, because the sea in question does not exist. But something like it survives in the experience of watching the ocean warm in late spring from a boat anchored in offshore waters, the way the light takes on a particular quality in April and May, the way schools of small fish begin appearing near the surface as if from nowhere, the way birds arrive at the water's surface and begin feeding in numbers that were not present a week before. The Seaway would have amplified all of this, because its shallow waters warmed faster than a deep ocean would, and because the nutrient cycling in those shallow waters was more efficient, and because the sheer biological richness of a sea ringed on all sides by low subtropical coastlines put more animals into it than a comparable area of open, deep ocean could have supported. As the elasmosaur moved north, the character of the water changed in ways that would have been perceivable even without the instrument of isotope chemistry. The watercolour shifted slightly, less of the deep blue associated with nutrient-poor tropical ocean, more of the green-tinged turbidity that indicates a bloom of phytoplankton in nutrient-rich water. The visibility decreased slightly, because more living material was suspended in the water column. The temperature gradient between the surface and the bottom became more pronounced as the surface warmed faster than the deeper water below it, creating a thermocline, a distinct layer where temperature dropped relatively sharply, that many prey species congregated just above or just below. The Seaway's shorelines would have been visible, at least distantly, for much of the migration's length. The corridor was wide, but not so wide that land was always beyond the horizon. On the western side, the rising uplift of the Sevier Orogeny, the mountain-building event that would eventually become the Rocky Mountains, provided a low but distinct horizon of higher ground, visible from the water on clear days. On the eastern side, the lower and more stable craton of the continent provided a shallower, more gradual coast, often lined with subtropical forest extending down to the water's edge. The Seaway was not, from within it, a featureless expanse of open water. It was a corridor with walls distant but present that would have provided a navigational reference point for an animal capable of using landmarks to orient itself. Whether elasmosaurs navigated using visual landmarks, geomagnetic fields, water temperature gradients, or some combination of all of these is unknown. The brain of an elasmosaur, known from a few internal skull casts, but not from actual preserved tissue, was small relative to body size by modern standards. But small brains are not necessarily simple ones, and the navigational capabilities of modern sea turtles and cetaceans suggest that an ocean-going reptile or mammal can maintain reliable directional orientation across very large distances using mechanisms that do not require the kind of cognitive complexity associated with large brain size. Here is a detail that has emerged from recent isotopic work on elasmosaur specimens from the northern formations, the Bear Paw Formation in particular, that bears on the question of how consistent the migration route was from year to year. The strontium isotope signatures in some northern specimens are remarkably consistent from one growth ring year to the next, suggesting that the same individual was returning to the same general body of water with the same characteristic strontium signature in successive years. The consistency is not perfect. There are small variations that suggest the animal was not navigating to a single, precise location the way a salmon returns to a specific stream, but the overall pattern is one of repeated return to a characteristic region season after season. This is what modern biologists call site fidelity, and it is a common feature of long-distance migrants in the modern world. Grey whales return to the same calving lagoons in Baja California year after year. Arctic terns return to the same nesting islands season after season, despite having crossed 2 poles to reach them. Leatherback sea turtles return to the same tropical beaches to lay their eggs, navigating thousands of miles of featureless open ocean to reach them with an accuracy that continues to astonish researchers who track them by satellite. Site fidelity implies memory, or at least a consistent biological program that reproduces the same journey reliably across successive years. For an elasmosaur living decades and making this journey 50 or more times, the route itself would have been as deeply embedded in its biology as breathing. Picture the animal now somewhere in the middle of the seaway's length, perhaps in the waters above what is now central Kansas. It is May, or something like May. The water temperature is approaching its optimal range for the prey blooms that will characterize the summer seaway. The shorelines are distant on both sides, too far to see clearly, though the light quality over the western horizon suggests the higher ground is there. The animal is moving at its characteristic pace, unhurried, the 4 paddles working in their alternating flight-like rhythm, the long neck held roughly level in the water ahead of the body, the small head slightly elevated to give the eyes the best possible angle on the water above. It is not thinking about the journey in any way that resembles thought. It is simply moving in the right direction because moving in the right direction is what its body tells it to do, and the direction and the movement are as old as the lineage it belongs to, as old as the seaway itself in any form that could have sustained it. The water around it is warm and green-tinged with life. The prey will be thick in the northern water within weeks, and there is a very long way still to go. Let it go. Follow it north, at its pace, through the warm light and the moving water. There is no hurry here. There never was. There is something about the far northern reaches of the Western Interior Seaway that appears in almost no account of the Cretaceous world, because it requires a deliberate effort to imagine conditions so different from anything in the modern temperate experience of the same geography. The water above what is now northern Alberta and the northwest territories of Canada, where the seaway extended toward its Arctic connection, was exposed to a phenomenon that most people today associate exclusively with Scandinavia or Alaska, the midnight sun. In summer, this far north the sun did not set, or rather it dipped toward the horizon, and then rose again without ever crossing below it, so that the long summer days of the high Cretaceous latitude went on and on and on, filling the water column with light at an angle that only changes this slowly, this gently, when the sun is tracing a nearly flat arc across a sky it barely leaves. This matters more than it might seem. Light is the engine of marine productivity. Phytoplankton, the microscopic single-celled organisms at the base of the marine food web, require sunlight for photosynthesis. In the modern high-latitude ocean, the explosion of primary productivity during the Arctic summer, when the sun provides continuous energy for photosynthesis around the clock, is so extreme that it represents one of the great seasonal events in marine biology, a burst of growth and reproduction so intense that it drives entire ecosystems into a brief, brilliant period of abundance before the returning darkness shuts it down again. The Cretaceous Arctic was not the modern Arctic. It was warmer, considerably warmer, and the organisms exploiting the summer light were adapted to different conditions than modern Arctic plankton. But the basic principle was the same, and its effects would have been similarly profound. An Elasmosaur arriving in the northern reaches of the Seaway in early summer would have entered a world undergoing a transformation of extraordinary richness. The continuous light was driving phytoplankton blooms across the shallower northern waters. Zooplankton, tiny animals that feed on phytoplankton, were reproducing in response to the abundance of food. Small fish were following the zooplankton, feeding in the warm surface waters under continuous sun. Larger fish and invertebrates were following the small fish. The whole system was stacking upward toward the surface in a way that it would not be doing in the same latitude in any other season. For an animal that hunts fish in the upper water column, this was a destination worth crossing a continent's worth of water to reach. The northern summer of the Western Interior Seaway, when the continuous light was driving productivity higher than at any other time or place in the Seaway's annual cycle, was probably one of the most consistently abundant feeding environments available anywhere in the Cretaceous interior ocean. The investment of the long northward journey, months of consistent paddling at walking pace, covering perhaps 8 or 9 miles per day, accumulating the distance the way compound interest accumulates money, slowly and then all at once, would have been repaid in a summer of feeding so productive that it could sustain the animal through the long return journey south. Here is a fact about the Cretaceous polar regions that belongs alongside the most counterintuitive in all of paleontology. Fossil trees recovered from sediments deposited within the Cretaceous Arctic Circle, above 80 degrees north latitude, where today there is permanent ice or permafrost, include species that paleobotanists identify as requiring year-round warmth to grow. There were breadfruit relatives at the North Pole. There were trees related to modern groups that cannot survive frost. And in the marine sediments of the same age from the same latitudes, there are the remains of animals that are identified in every other context as warm water marine organisms, corals, some species of ammonites, certain fish groups, surviving and reproducing in waters that, by the chemistry of the sediment around them, were seasonally cooled but never frozen. The implication is that the northern end of the migration corridor was not the forbidding, cold, alien environment that modern geography might suggest. It was, in the Cretaceous summer, a place of extraordinary warmth and productivity, a place where an animal accustomed to warm water could move, feed, and rest without experiencing a significant deterioration in conditions relative to the southern waters it had started from. The gradient the migration exploited was not a gradient from comfortable to barely tolerable. It was a gradient from productive to extraordinarily productive, and the destination was the more abundant of the two ends. What did it look like, the northern seaway in summer? The water would have been clearer than the turbid southern reaches during peak bloom periods, clearer the way open water is clear when you are far from a shoreline, with a particular quality of depth colour that is hard to describe to someone who has not seen it. Green at the surface, where the plankton were thickest. Blue-grey deeper down, where the light scattered and diminished. The bottom would have been invisible from the surface except in the very shallowest parts near the shore. The shore itself, in the north, was lower and flatter than the western shoreline with its hint of rising mountains. It extended into swampy, low-lying coastal forest where dinosaurs moved in the undergrowth and herds of hadrosaurs came to the water's edge to drink. Hadrosaurs at the water's edge deserve a brief mention here because they represent a category of animal the migrating Elasmosaur would have encountered regularly at the northern end of its journey, large terrestrial animals coming to the shallow margins of the seaway. These were herbivorous dinosaurs, some of them reaching 30 feet in length, that moved in herds through the coastal forests and wetlands of the Cretaceous North America. They had no reason to venture beyond the shallows, and an Elasmosaur had no interest in anything at the surface that weighed several tons, and had no presence in the water column. But the awareness that the coast was there, visible from the surface on clear days, the shapes of large animals moving in the vegetation at the waterline, would have been part of the sensory landscape of the northern summer. What about the nights, or what passed for nights in the northern summer? Here the question becomes interesting in a way that involves the biology of vision in large marine reptiles. The Elasmosaur's large eyes are designed for gathering light in relatively dim conditions. A large eye collects more photons per unit time than a small eye, which is why deep water fish tend to have very large eyes relative to body size, and why many predatory marine animals that hunt at varying depths have evolved larger than average eyes. In the continuous light of the northern Cretaceous summer, this eye design would have been more useful during the lower light hours, when the sun was at its lowest angle, than during the midday hours of intense surface illumination. There may have been a rhythm to the feeding day, shaped by the gradual dimming of light to its nighttime minimum, and the behavior of prey species that moved through the water column in response to light intensity. Many modern schooling fish perform what biologists call diel vertical migration, moving toward the surface as light dims in the evening and descending again as light intensifies toward morning. The trigger is light intensity, and the behavior is a predator avoidance strategy. Surface waters are more dangerous in bright light because predators can see better. In the dimmer light of evening and early morning, the fish come up to feed on plankton-rich surface waters with less risk. If Cretaceous schooling fish followed a similar pattern, then the Elasmosaur's optimal hunting time in the northern summer would have been the low-light hours when prey was concentrated near the surface, and the animal's large eyes gave it maximum sensitivity. There is no way to confirm this from the fossil record. The behavior of prey is even harder to reconstruct than the behavior of predators, and the specific feeding habits of Cretaceous schooling fish are known only in the roughest outline. But the visual anatomy of the Elasmosaur is consistent with an animal capable of hunting effectively in low-light conditions, and the vertical migration behavior of schooling fish appears to be ancient enough to have been present in some form during the Cretaceous. The image that emerges is of an animal that perhaps fed most actively in the dimmer hours of the northern summer night, not quite dark, never quite dark this far north in summer, when the prey was at the surface and the eyes could work at their best. The duration of the northern summer stay is not known with precision. Modern long-distance marine migrants typically remain at their summer feeding grounds for 2 to 4 months, feeding heavily before the conditions that drove them there begin to reverse. The seasonal signal that would have told an Elasmosaur it was time to begin moving south again would have been the same signal that triggered the northward journey, a change in light, in water temperature, in the abundance and behavior of prey. As autumn advanced into the northern seaway, the continuous light would have begun to shorten for the first time since spring. The surface waters would have begun cooling. The great productivity bloom would have peaked and begun to wane. The timing of the southward turn is significant in a way that bears on a question of Elasmosaur biology that remains incompletely answered. If Elasmosaurs gave birth to live young, and the evidence suggests they did, then the timing and location of birth would have been determined by the migration cycle. A birth in the north, during the summer feeding season, would have placed a newborn animal in the most abundant feeding environment available. A birth in the south, in the warm winter waters where the annual cycle began, would have placed it in warmer but less immediately productive water. The single large offspring implied by the South Dakota specimen could, in principle, have been carried through the northern summer by its mother and born at the beginning of the southward migration, entering the water already capable of following the return journey. This is speculation, informed by analogy with modern marine migrants who time their reproduction to the most favourable point in the annual cycle, but it is the kind of speculation that the evidence permits without contradicting, and it adds another dimension to the picture of the northern summer. Not just a feeding destination, but possibly a birth destination, a place where the richest waters coincided with the turning point in the year, where new life entered the seaway at the moment of its greatest abundance. Let that image settle for a moment before we begin the turn south. The water is warm, the light is extraordinary, continuous, the quality of late afternoon stretched across the whole of the sky, and somewhere in the middle of it, a small head rises on a long neck, draws a breath in the continuous summer light, and begins, very slowly, to orient toward the south. The Western Interior Seaway was not a quiet place, even for an animal as large as an Elasmosaur. It shared its waters with a community of predators whose fossilized remains fill museums across the American and Canadian Great Plains, and the relationship between the long-necked traveller and those predators is preserved not merely in reconstructed species lists, but in the bones themselves, in bite marks and healed injuries, and the evidence of encounters that ended in various ways, some of them worse than others. This chapter is about that community, about what moved through the same water at the same time, and about what the bones tell us of the interactions that occasionally occurred. The most numerous and most diverse predators of the late Cretaceous Seaway were the mosasaurs. By the closing millions of years of the Cretaceous, they are diversified into dozens of species occupying nearly every ecological role in the Seaway's food web. The largest of them, Mosasaurus hoffmanni, reached 57 feet in length, longer than the Elasmosaur, and was capable of generating bite forces that could crack bone. Tylosaurus, another large mosasaur common in the Western Interior Seaway, reached 40 feet and possessed a reinforced snout that researchers believe it used to stun prey with forward strikes before closing its jaws. Platecarpus was smaller, more streamlined, and built for sustained pursuit through open water in a manner reminiscent of a large tuna or a porpoise. What did mosasaurs make of elasmosaurs? The fossil evidence provides some answers. Elasmosaur bones carrying mosasaur bite marks have been recovered from the Niobrara and Pierre Shale formations, establishing that attacks did occur. The bite marks are not ambiguous. The tooth spacings and curvatures match mosasaur dentition, and the bone remodeling around some of the marks indicates that at least some individuals survived the attack, lived long enough for the bone to begin healing, and continued the migration with the evidence of the encounter preserved in their skeleton. A healed bite mark on a surviving animal is one of the more quietly eloquent facts in paleontology. It means the animal was hit, hard, by something with very large teeth, and it kept going. The encounters were not necessarily predatory and intent on every occasion. Mosasaurs were opportunistic hunters, taking what they could over power. A full-grown elasmosaur, at 30 to 45 feet in length and substantial bulk, would have been a significant challenge even for a large mosasaur. The neck, long as it was, offered a target that a mosasaur could potentially seize, but the neck also allowed the elasmosaur to detect the approach of a large body at a distance and respond before the distance closed. Whether the response was evasive or defensive, whether elasmosaurs dove deeper or scattered their school hunting formation or simply altered their direction of travel, cannot be determined from the bones. But the survival of marked individuals suggests that the encounter was survivable, and that being hit once did not necessarily mean being killed. Juveniles were considerably more vulnerable. A newborn elasmosaur, perhaps a quarter of its adult length, would have been well within the size range that mosasaurs routinely consumed, and the migration corridor passed through the full range of mosasaur habitats from south to north. This is one of the reasons researchers who study elasmosaur population biology suggest that juvenile survival rates were very low. The journey that an adult could complete with a reasonable expectation of arriving intact was, for a juvenile accompanying the first migration of its life, an extremely dangerous passage. The Seaway did not offer sanctuary. It offered opportunity and danger in the same water. Alongside the mosasaurs, the great shark Cretoxorhina mantelli occupied the Seaway in considerable numbers during the peak period of elasmosaur abundance. Cretoxorhina was not a small animal. Full adults reached 25 feet in length, roughly as long as a modern great white but substantially more robust in build, with a body designed for sustained high-speed pursuit rather than ambush. Its teeth were smooth-edged and blade-like, arranged in 7 replacement rows so that a broken tooth was immediately succeeded by another, and it could sustain swimming speeds that modern reconstruction suggests exceeded any living shark species. The relationship between Cretoxorhina and elasmosaurs in the Seaway is documented by fossil evidence from multiple specimens. Cretoxorhina teeth have been found associated with elasmosaur remains in contexts suggesting predation or scavenging. Given the shark's size and speed relative to the elasmosaur's limited acceleration, an adult Cretoxorhina would have been a more consistent threat than a mosasaur in open water situations, where the shark's straight-line speed advantage was decisive. The elasmosaur's best defense in such an encounter would have been depth, going deep quickly enough to remove itself from the surface zone where Cretoxorhina hunted most effectively. Here is one of the pieces of elasmosaur anatomy that is rarely discussed in the context of predator avoidance, but that deserves attention in that context. The neck, long as it is oriented horizontally during normal swimming, extending ahead of the body at roughly the same depth as the torso. When an elasmosaur dives, the body pitches forward. The angle of the paddles changes, and the whole animal descends at an angle controlled by the orientation of the forepaddles. The neck during a dive does not pitch steeply downward the way you might imagine. The skeletal and muscular architecture of the 72 cervical vertebrae is not designed for extreme vertical flexion. The animal descends more like an airplane banking into a shallow descent than like a diving bird tucking its head and plunging. This means the dive is controlled and sustained rather than explosive, which is perhaps not ideal for escape from a fast pursuer, but does mean the animal could reach safer depth reliably, without any of the frantic energy expenditure that an escape response would otherwise require. There was a third major predator in the seaway that the Elasmosaur would have shared its migratory corridor with, and this one is worth pausing to describe because it represents a different kind of danger, one that came not from a direct attack, but from the sheer scale of its presence and the way it affected the behaviour of everything around it. Xiphactinus audax, the giant bony fish of the Cretaceous Seaway, reached 20 feet in length and was equipped with a large, forward-projecting lower jaw lined with long, spike-like teeth. It was a pursuit predator capable of considerable speed, and like the Elasmosaur, it was primarily a fish hunter, though it was perfectly capable of taking much larger prey when the opportunity presented itself. Xiphactinus is famous in paleontology for a different reason from most prehistoric animals. It is famous for what was found inside it. A specimen recovered from the Niobrara Formation in Kansas, one of the most celebrated individual fossils in American paleontological history, was found with another fish, Gylicus arcuatus, measuring about 6 feet in length, still essentially intact inside its stomach cavity. Digestion had barely begun when the Xiphactinus died, suggesting that the swallowed fish, larger than expected, had struggled sufficiently after being swallowed to fatally injure its captor from the inside. Both animals were preserved together in the stone as a result. The relevance to the Elasmosaur's migration is that Xiphactinus occupied the same broad habitat and the same food resources. Where the fish that the Elasmosaur depended on were abundant, Xiphactinus would also be present, feeding on the same schools with its very different body plan and hunting strategy. The Seaway's fish populations were shared resources, and the long-necked traveller was not the only large predator making use of them along the length of its annual corridor. The competition was not necessarily direct or conflictual. The animals were hunting the same prey in different ways, and the Seaway was large enough to absorb both of them without requiring constant territorial conflict. But the shared food resource meant that periods of unusual scarcity affected everyone. There is one more predator worth mentioning, because its bones occasionally turn up in the same formation layers as Elasmosaur remains, and because the relationship between them illustrates something important about how the Seaway's ecology was organised. Squalicorax, a smaller shark reaching perhaps 8 to 10 feet in length, was more of an opportunistic scavenger than an active pursuit predator of large prey. Squalicorax teeth are found in association with large carcasses of all kinds in the Seaway formations, including mosasaurs, large fish, and plesiosaurs. They were the clean-up crew of the Seaway, processing the dead and the dying with efficiency. They would have been present wherever large animals concentrated, and the migration corridor of the Elasmosaur would have been a reliable location for concentrations of the large prey on which they scavenged. What the Elasmosaur made of all this, what its experience of moving through a water that contained all of these other large, dangerous animals was like, is not something that can be directly known. But the behavioural picture that emerges from the anatomy and the fossil evidence is of an animal that moved through risky water with a particular set of adaptations for managing that risk. The long neck kept the large body farther from the surface where most attacks originated. The large eyes provided early detection of approaching danger. The depth capacity of the paddle-driven locomotion provided an escape route that a surface-oriented pursuit predator could not easily follow. And the sheer size of the adult animal, approaching or exceeding the length of all but the largest mosasaurs, provided a degree of deterrence that made any attack a significant undertaking rather than a routine one. The evidence of healed bite marks is, in this light, not just evidence of vulnerability, it is evidence of survival, of an animal that was hit and kept going, that carried its wound north and south through subsequent migrations, that added another year's growth ring above the injured bone, and another season's worth of chemical signature to its isotopic record. The marks in the bone are not tragedy. They are testimony to the durability of the long-necked traveller, to its capacity to absorb a serious encounter and continue on its way, undiverted from the great seasonal rhythm that organised its entire existence. The Seaway was not safe, but it was known, and knowing a danger even without the ability to reason about it is its own form of preparation. If you are drifting now, let yourself go. Subscribe so the next story is waiting when you return. Sleep well. The neck of an Elasmosaur has attracted more speculation than almost any other feature of any other prehistoric animal, and much of that speculation has been wrong. The error is an understandable one. A neck 14 feet long attached to a body 40 feet from nose to tail, attached to a head the size of a sheep's, invites the question, what is it for? And the first answer that presents itself to the modern imagination, that it is used to strike fish from above, sweeping down from a great height like a heron's neck striking into shallow water, turns out, on closer examination by people who have studied the mechanics carefully, to be almost certainly mistaken. The confusion is partly historical. Early reconstructions of plesiosaurs, drawn in the 19th century when the first reasonably complete skeletons became available, showed the neck arched dramatically upward above the body like a swan's, with a head elevated high above the waterline and capable of being brought down in a rapid strike. These images were vivid and memorable, and they entered the public consciousness with a persistence that no subsequent correction has quite managed to dislodge. But the anatomy does not support the image. The cervical vertebrae of elasmosaurs are not designed for the extreme dorsal flexion, the upward arching, that the swan neck posture requires. The muscles attached to those vertebrae, as inferred from the attachment scars on the bones, are not the muscles of an animal that held its head high above the water. The most widely accepted reconstruction among current researchers shows the neck held roughly horizontal during normal swimming, extending ahead of the body at approximately the same depth as the torso. The head at the tip of this extended neck would have been travelling through the water about 14 feet ahead of and slightly above the body, giving the animal a considerable reach in the forward direction. The neck could flex laterally, side to side, with more freedom than it could flex vertically, which is consistent with an animal that was sweeping its head through a horizontal plane, tracking and intercepting prey that was moving across its path rather than striking down from above. What this means for the hunting technique is worth imagining carefully. Picture an elasmosaur approaching a school of small fish from below and behind. The body, large and dark and moving steadily, is far enough below the school that the fish have not yet reacted to its approach. The neck extends ahead of the body at a shallower angle, threading upward through the water column with considerably less cross-section than the body behind it. A neck 14 feet long and a foot or so in diameter presents much less visual disturbance to a school of fish than a body 4 or 5 feet across and 10 feet long. The head at the tip of the neck, smaller still, enters the school with minimum disturbance before the fish have processed the approach of the much larger structure following it. The jaw closes. One fish, or perhaps two if the school is dense enough, is secured between the interlocking teeth. The neck retracts slightly, not the full 14 feet, but enough to position the prey for swallowing. The head tilts, orients the fish head first into the throat, and the prey is gone. The school is already dispersing in alarm, but the elasmosaur is already repositioning, already on its approach to the next pass. The whole sequence is deliberate, unhurried, and based on concealment and precision rather than speed or force. There is a second function of the long neck that has received attention in recent years, and that makes sense when you think about the three-dimensional structure of the water column. Fish schools in open water are not distributed randomly. They are concentrated in layers, clustered at or near the thermocline, where temperature changes rapidly with depth, or at the chlorophyll maximum, where phytoplankton are most dense. These layers may be thin, a few feet thick, and they may be at depth that vary considerably across the day and across the season. An animal with a 14-foot neck can sample a large range of depths without significantly repositioning its body. In practical terms, this means an elasmosaur could cruise at a comfortable swimming depth, perhaps 20 or 30 feet below the surface, while extending its neck upward or at an angle to probe fish-rich layers at different depths within that range. The body maintains a stable, energy-efficient trajectory while the neck does the prospecting, reaching up to test the surface layers, angling down slightly to check the thermocline layer, sweeping laterally through the current seam where fish sometimes concentrated. The neck is, in this interpretation, a sensory extension as much as a strike mechanism, a mobile probe that can sample a large volume of water without requiring the whole animal to maneuver through it. This interpretation is supported by the structure of the Elasmosaur's sensory anatomy. The nasal openings in some Plesiosaur skulls appear to connect to passages that could function as flow detectors, organs sensitive to the pressure waves created by schools of moving fish, similar in principle to the lateral line system that most fish use to detect water movement around them. Whether Elasmosaurs possessed this kind of hydrodynamic sensing is uncertain, but the skull anatomy in several species is consistent with it, and an animal hunting by extending a long neck into dark or turbid water would benefit enormously from the ability to detect prey by water movement before visual contact was possible. What is rarely mentioned in discussions of Elasmosaur feeding is the role of the gastroliths, the stomach stones, in the context of what has just been described. Gastroliths turn up in many Plesiosaur specimens, sometimes as many as 200 smooth stones clustered in the abdominal region where the stomach would have been. The traditional interpretation is that these stones served as a grinding mechanism, helping to break down the hard shells of ammonites or crustaceans that the teeth were not designed to process. This explanation works for some animals that swallow gastroliths, like modern crocodilians, but the mass of stones found in some Elasmosaur specimens is large enough to raise questions about whether grinding alone explains them. The alternative hypothesis, ballast for buoyancy control, makes particular sense in the context of the feeding strategy just described. If an Elasmosaur needed to maintain a specific depth without expending muscular effort, if it needed to hover at the level of the thermocline or the chlorophyll maximum and extend its neck upward while its body remained still, then a collection of heavy stones in the abdominal cavity would help it do exactly that. The stones would pull the centre of gravity downward, counteracting the slight positive buoyancy that the lung air in an air-breathing animal would otherwise create, allowing the animal to maintain a chosen depth passively. The body becomes an anchor, and the neck is free to work above it without the disturbance that continuous swimming would create. There is one more aspect of the neck that deserves attention before we move on, and it is the one that is most directly connected to the migration. 14 feet of neck held horizontal in the water ahead of the body gives the animal a roughly 14-foot head start on detecting what is in the water ahead. The sensory organs, the eyes, the possible flow detectors, the nostrils that could sample the chemical composition of the water being moved toward, are 14 feet ahead of the bulk of the animal. For an animal navigating by water chemistry, by temperature gradient, by the chemical signatures in the water that tell it whether it is in the right part of the seaway or not, this advanced detection capability is significant. Modern long-distance migrants navigate using a combination of mechanisms: geomagnetic sensing, star patterns, sun angle calculation, chemical gradients in the water, and memory of previously travelled routes. The relative importance of these mechanisms varies by species and by the specific navigational challenge being solved. For an Elasmosaur navigating the length of a 1,000-mile corridor twice a year, the most reliable guide would have been the temperature gradient, the simple fact that warmer water was to the south and cooler water was to the north, combined with chemical signatures that distinguished the more marine southern water from the more terrestrially influenced northern water. A 14-foot neck extending ahead of the body is a remarkable sampling device for all of these signals, continuously testing the character of the water ahead of the animal's main body before the body has committed to moving through it. Think of it this way. The neck is not merely a tool for catching fish. It is a tool for navigating, for sampling, for maintaining awareness of the water's quality at a range of depths, without exposing the whole animal to that range of depth simultaneously. It is a multi-purpose instrument that happens to end in a jaw, and the jaw is perhaps the least important part of it, from the perspective of the animal's long-term survival. Fish caught, fish swallowed, one meal at a time, this is necessary and routine. But arriving in the right place at the right time of year, following the thermal gradient of a 3,000-mile corridor, with sufficient accuracy to reach the northern summer feeding grounds, before they peak and leave before they collapse. This is what the whole migration depends on, and the neck is part of the system that makes it possible. It is a gentle realization, this one, that the most dramatic anatomical feature of one of the most remarkable animals in the Cretaceous ocean is, at its heart, an instrument of patience and precision rather than of violence. The neck did not evolve to intimidate. It did not evolve to allow dramatic striking attacks from the air. It evolved because the animal that had a slightly longer neck could reach slightly more fish, could sample slightly more of the water column, could detect prey, and navigate with slightly more accuracy, and could pass these slight advantages to its offspring across generation after generation until the length became extreme. Extremity in nature is always the accumulation of modest advantages. The neck is long because being long, very gradually and over a very long time, was the right answer to the questions the Seaway kept asking. There is a moment in the northern summer when the light begins to change in a way that is almost imperceptible to anything without a very precise relationship to the quality of the sky. The sun, which has been tracing its nearly flat arc just above the northern horizon even at what passes for midnight, begins to dip a little lower. The lowest point of that arc drops a degree or two each week, and the lowest point begins to actually touch the horizon for a brief interval, and then briefly crosses below it, and the first real darkness in months comes to the northern seaway in a brief, violet interval that lengthens a little every night. The water that was warm is still warm, but the direction of change is reversed. It is beginning, almost imperceptibly, to cool. This is the signal that begins the return. Not a dramatic cooling, not a sudden chill that sends everything moving at once, but the first inflection of a gradient that has been running in one direction for months and is now shifting. The Elasmosaur does not have a concept of the changing of the season. It has a body that is sensitive to the temperature of the water it is in, and a biological system that interprets a cooling trend in formerly warm water as a signal to begin moving in the direction where the water is warmer. The direction where the water is warmer in autumn is south. The migration has reversed. The return journey is in many ways the same as the outward journey, covered at the same pace, through the same general corridor, using the same thermally guided navigation that carried the animal north in the spring. But there are differences in the character of the water that make the southward journey a different experience from the northward one, and these differences are worth paying attention to because they tell us something about the annual rhythm of the whole system. The seaway in early autumn is not the same seaway it was in early spring. The summer's productivity has passed through the food web, and the animals that spent the summer in the northern waters are fat and rested, and have the energy reserves for the long return journey that they did not begin the year with. The prey too is in a different state. The fish schools of the northern summer, which fed on the extraordinary bloom of plankton under the continuous light, have grown and reproduced through the summer months. In early autumn, before the cooling accelerates enough to drive them south themselves, the northern fish are at their largest and most numerous. The Elasmosaur, beginning its southward migration, is moving through the richest fish resource the seaway will offer at any point in the year. It can afford to move slowly through the northern water, feeding as it goes, not driven by urgency or need, but simply taking advantage of what is available as it passes through. This feeding as travelling pattern is common among modern long-distance marine migrants, and is thought to be important for building the energy reserves required for the lean middle sections of long migrations, where prey is less concentrated, and the animal must rely more heavily on the stored fat than on current intake. The southward journey through the northern seaway in early autumn would have provided a natural opportunity for exactly this kind of energy loading, moving through water that was still rich, feeding consistently, adding the fat reserves that would carry the traveller through the longer, emptier stretches of the mid-seaway corridor in late autumn. The mid-seaway, somewhere above what is now Kansas and Nebraska, was a different kind of water in autumn from what it had been in spring. The great spring bloom was long past, and the summer's biological activity had left the water in a state of productive afterglow, not as rich as the peak periods, but still supporting good populations of the fish and cephalopods that the Elasmosaur depended on. The water temperature in the middle latitudes was declining now, cooling a few degrees below the summer peak, and the character of the light was visibly different, lower in the sky, more golden in quality, the kind of light that in the modern world is associated with September afternoons in the American heartland. Under that autumn light, the seaway looked different than it had under the high summer sun. The watercolour shifted toward a deeper blue as the phytoplankton bloom diminished and the turbidity dropped. On clear days, the sun's angle cast the water in a way that made the ripple patterns on the surface visible from below as an ever-changing net of light and shadow. The chalk bottom, visible in the shallower parts of the corridor, showed its characteristic pale colour with more clarity than in the productive green water of summer. There was a quality of stillness to the autumn seaway that the summer had not had. Not empty stillness, but the settled, satisfied quality of a place that has been fully alive for months and is now beginning to rest. The Elasmosaur moved through all of this at its characteristic pace, 2 to 3 miles per hour, 8 or 10 miles a day, the paddles working in their alternating rhythm. At this pace, crossing from the northern end of the seaway to the southern end would have taken roughly 3 to 4 months. If the southward turn came in early September by the seasonal reckoning of the modern calendar, then the animal would have been arriving in the warm southern waters around December or January, the depths of the Cretaceous winter in the temperate sense, though in the south of the seaway this would have been the mildest reduction in temperature, the water barely cooler than it had been in the hottest summer months. Here is something about the return journey that is rarely discussed. It was not necessarily the direct reversal of the outward route. Modern long-distance migrants often use different routes for their outward and return journeys, exploiting the seasonal pattern of prevailing currents. The different timing of productivity blooms along different paths, and the availability of food at different times of year along different corridors. The Western Interior Seaway, while its general north-south orientation constrained the overall direction of travel, was wide enough to permit significant variation in the specific path through it. An animal might move down the eastern side of the seaway on the return, where the influence of the rivers draining the eastern craton produced a different water chemistry and a different prey community from the more open, marine-influenced western side. The isotopic evidence from individual specimens is not yet detailed enough to reconstruct the specific path of any individual Elasmosaur with that kind of precision, but the range of isotopic signatures seen in different specimens from the same general time period and formation is wide enough to suggest considerable variation in where different individuals spent their time within the seaway's breadth. This is not surprising. Modern populations of long-distance migrants show individual variation in route, timing, and destination, shaped by a combination of inherited tendencies and learned experience. An Elasmosaur that had discovered, in a previous year, that the eastern side of the seaway in autumn was particularly productive might have biased its return route in that direction in subsequent years. The migration corridor was broad enough to accommodate individual strategies. As the return journey proceeded south, the water temperatures that the animal encountered would have been gradually increasing rather than declining, because the southward movement was outpacing the southward progression of the cooling trend. The animal was, in effect, running slightly ahead of autumn, moving fast enough to stay in water that felt like late summer, even as the calendar progressed through October and November. This is, again, exactly the kind of behaviour seen in modern marine migrants, moving through a seasonal gradient in a direction that keeps the animal in its preferred temperature range as the gradient shifts. There is a question about the return journey that the fossil record cannot directly answer, but that the animal's physiology raises. Did Elasmosaurs feed differently on the return journey than on the outward one? On the outward journey in spring, the animal was moving through a seaway that was warming and becoming more productive as it travelled north, with the peak productivity still ahead of it. On the return journey, the peak was behind it, and the animal's energy reserves from the northern summer were at their highest. The return might therefore have been a period of somewhat less intense active feeding, with the animal relying more on stored reserves and feeding opportunistically rather than systematically. This is consistent with what is known about the energetics of long-distance migration in modern animals. Sea turtles making transoceanic migrations have been recorded feeding relatively little during certain legs of their journey, drawing on stored fat reserves accumulated during intense feeding periods and converting that stored energy into the sustained muscular effort of continuous swimming. If Elasmosaurs operated on a similar energy economy, then the autumn return, following a summer of intense northern feeding, might have been a period of relatively effortless travel, the paddles working steadily, the stored energy providing the fuel, the animal gradually working its way south toward the warmer water where the cycle would begin again. The destination in the south was not merely a warm place but likely a specific region with specific characteristics. The isotopic signatures of southern specimens, those recovered from formations deposited in the warmer, more tropical southern reaches of the seaway, are consistently different from the northern signatures in ways that suggest these animals were genuinely in different water environments during different parts of the year. The southern water in winter was warm, relatively still, and influenced by the tropical marine conditions of the Tethys connection to the south. It was a resting place in the seasonal sense, less intensely productive than the northern summer, but comfortable, stable, and safe enough for the recovery and preparation that preceded the next spring's departure. Arrive there now, in the imagination. The water is warm. The light comes down at a lower angle than it did in the northern summer, but it stays gentle and golden through the long winter days, and the temperature is everything the long journey asked for. The Elasmosaur settles into the southern water with the quality of something that has returned to where it belongs. The paddles slow, the long neck drifts in the mild current. The small head turns once, twice, and then stills. The cycle is complete, the year has turned, and in a few months, when the first signals of the spring reversal begin to accumulate in the quality of the light and the direction of the temperature gradient, the whole long movement will begin again, north, steadily and unhurriedly north, through the warm corridor of a sea that no longer exists but that was, for the animals that move through it, as familiar and as constant as the rhythm of breathing. There is a mystery in the belly of every Elasmosaur specimen that preserves its abdominal contents, and it is a mystery that has been discussed and debated for well over a century without arriving at anything like a settled resolution. The mystery is smooth stones, dozens, sometimes hundreds, of water-worn, perfectly smooth pebbles and cobbles clustered in the region of the digestive tract, preserved in the same fine-grained sediment that preserved the bones around them, clearly associated with the animal and clearly not part of the normal sedimentary environment in which the animal died and was buried. These are the gastroliths. Animals that swallow stones are not unusual in the modern world. Modern crocodilians ingest stones regularly, and a number of bird species do as well. The stones in these modern animals serve a mechanical function. They sit in the muscular gizzard and grind food material against each other and against the gizzard wall, processing plant material or hard-shelled prey that the teeth cannot reduce to a swallowable consistency. This interpretation has been applied to Elasmosaur gastroliths by default. They ground up shelled prey, ammonites or crustaceans, processing them in the gut the way a bird's gizzard processes grain. The problem with this interpretation is that it doesn't quite fit the other evidence. The teeth of Elasmosaurs are not designed for dealing with heavily armoured prey. The slender, interlocking tooth design is optimised for gripping slippery fish, not for cracking ammonite shells or crustacean carapaces. The stomach contents associated with Elasmosaur specimens, where food remains are preserved well enough to identify, include fish and cephalopod material rather than heavily shelled prey. If Elasmosaurs were primarily fish hunters, as the tooth design and preserved stomach contents suggest, the grinding stone interpretation becomes less compelling, because fish do not require grinding. The alternative interpretation, ballast for buoyancy control, was proposed seriously in the scientific literature in the 1990s and has been the subject of ongoing debate since. The argument runs as follows. An air-breathing animal that spends the great majority of its life submerged faces a basic buoyancy problem. The lungs contain air, and air is lighter than water, so an air-breathing animal tends to float. For an animal that needs to maintain a specific depth in the water column without constant muscular effort, this positive buoyancy is a problem. Stones in the gut shift the centre of gravity downward and toward the denser end of the body, partially counteracting the positive buoyancy created by the air in the lungs and allowing the animal to maintain a chosen depth with less muscular expenditure. This function would be particularly valuable for an animal that spent a lot of time cruising at moderate depths, extending its neck upward to probe the fish-rich upper water column while maintaining a stable body position below. The stones would not eliminate the buoyancy problem entirely. The physics of the situation require more stone mass than any reasonable gut capacity could provide to make an air-breathing animal genuinely neutrally buoyant, but they could reduce the muscular effort required to hold a chosen depth from significant to modest, which over the course of a very long migration would represent an important energy saving. There is a third hypothesis, less widely discussed but worth considering, that the gastroliths served a social or communicative function, that the sound of stones clicking together inside the body cavity during movement or during certain behaviours was a form of acoustic communication between individuals, audible underwater over significant distances. This hypothesis is the most speculative of the three and lacks direct supporting evidence, but it is not entirely without biological precedent. Some modern animals do use sounds associated with bodily function. The clicking of vertebrae, the rumbling of digestive sounds, in social communication. The notion that a long-necked animal making a solo journey of several thousand miles might also use its stomach stones to signal to others of its kind at a distance is appealing in the imagination, even if it cannot currently be confirmed. What is not in doubt is the effort involved in acquiring the stones in the first place. The Seaway's deeper waters, where elasmosaurs spent most of their time, were not rocky. The seafloor was chalk and fine-grained calcareous sediment, the accumulated remains of billions of microscopic shells laid down across millions of years. Smooth, hard cobbles of the kind found in elasmosaur abdominal regions would have required a trip to a rocky shoreline or riverbed to acquire, and the smooth, water-worn quality of the stones indicates they came from running water or wave-worked coastal environments, not from the seafloor of the open seaway. This means that at some point in their lives, elasmosaurs visited shallower, shore-adjacent waters, river mouths, coastal shallows, wave-worked beach environments, and deliberately swallowed suitable stones. This is not a trivial behaviour for an animal whose entire life was organised around open water existence. The journey to the shore to collect stones, and the subsequent care involved in retaining them, rather than passing them through the digestive tract, suggests a level of physiological management around this behaviour that implies the stones were serving an important function, important enough to justify the effort and the brief exposure to the dangers of shallow coastal waters. Here is a detail that is almost never mentioned in any popular account of elasmosaur biology, but that follows logically from the gastrolith evidence. If the stones were collected in coastal waters, and if the animal spent most of its adult life in open water far from coasts, then the collection of gastroliths must have taken place during a specific phase of the animal's life cycle, most likely the juvenile period, before the adult pattern of long-distance open water migration was fully established, or it took place during specific shore-adjacent phases of the migration when the animal passed through coastal zones at the northern or southern ends of the corridor, where river systems met the seaway and rocky substrates were available. The northern end of the seaway, where the corridor opened toward the shallower, rockier coastal environments of the Cretaceous Arctic, would have been an ideal location for gastrolith collection. River systems draining the northern uplands would have deposited smooth cobbles and pebbles along their courses and at their mouths where they entered the seaway. An elasmosaur pausing to feed in the productive northern summer waters, moving through the shallower near-shore zone in pursuit of the inshore fish populations, would have had the opportunity to move across rocky or gravelly substrates where suitable stones were available. The image of a long-necked animal systematically ingesting smooth stones from a rocky riverbed or a pebble beach is one of the most unexpectedly domestic moments in all of elasmosaur biology. It interrupts the grand narrative of the ocean migration with something very small and very careful, a large animal moving slowly through ankle-deep water in the northern summer, the long neck dipping again and again to select a particular smooth pebble, swallow it, move on. The criteria for selection are not known. The exact size range of stones in different specimens varies, suggesting that stones of a range of sizes were acceptable, but the smooth worn quality is consistent, suggesting that rough, unweathered stones were avoided. The gastroliths that survive in fossil specimens have been subjected to the same processes of mineral replacement as the bones around them. In many cases they have been chemically analysed, and the results offer yet another window into where the animal had been. The mineralogy of a stone, its exact chemical composition and crystalline structure, reflects the geology of the environment where it was eroded and rounded. Stones from rivers draining ancient granite uplands have a different chemical signature from stones derived from sedimentary limestone formations. By matching the mineralogy of elasmosaur gastroliths to geological source areas, researchers can sometimes determine approximately where an individual animal collected its stones, and therefore where it was at a particular phase of its life. This analysis has not been applied to elasmosaur gastroliths as systematically as isotope analysis has been applied to the teeth and bones, but the few studies that have been done suggest that stone sources are consistent with the northern, more geologically complex end of the Seaway's corridor, where older and more mineralogically diverse geological formations provided a wider range of stone types than the predominantly chalky southern formations. This is consistent with the idea that stone collection happened in or near the northern summer feeding grounds, adding another reason, if one were needed, for the annual journey north. The stones, then, are not merely a curiosity. They are another thread in the complex fabric of the migration's biology, connected to buoyancy, to feeding strategy, to the specific geography of the migration corridor, and to the behavior of an animal at a specific place and time in its annual cycle. They are small and smooth and heavy, and they made the long journey south in the belly of the animal that carried them, and they rested on the seafloor of the warm southern water through the winter while the animal fed and rested above them, and they made the long journey north again in the spring. They were carried 10,000 miles a year, year after year, for the whole of the animal's life. If patience has a physical symbol, it might be a smooth stone swallowed in a northern river and carried, without being released, through every season of a very long life. Elasmosaurus was not alone. It would be a mistake to speak of the Elasmosaur migration as if only one species was involved, or as if the Western Interior Seaway were the exclusive domain of a single lineage of long-necked reptiles. The Cretaceous was generous with its plesiosaurs in a way that the modern world, which has nothing that exactly resembles them, makes difficult to appreciate. By the late Cretaceous, the plesiosaurs had diversified into two broad body plans that are easy to think of as two solutions to the same general problem of making a living in open water as a large air-breathing reptile. On one side of the family were the Elasmosaurids, the long-necked forms with small heads and fish-catching teeth, of which Elasmosaurus platurus is the largest and most famous North American example. On the other side were the polycotylids, sometimes called short-necked plesiosaurs or pliosaurs in popular accounts, which had much shorter, thicker necks, large heads, and powerful jaws designed for dealing with larger, harder prey. Both groups occupied the Western Interior Seaway simultaneously, and both left abundant fossil remains in the Niobrara and Pierre Shale formations. Among the long-necked elasmosaurids in the Western Interior Seaway, Elasmosaurus itself shared the water with several related forms. Styxosaurus, another long-necked elasmosaurid from the Niobrara formation, reached lengths comparable to Elasmosaurus and possessed a similar extremely elongated neck, though the exact vertebral count in Styxosaurus differs from Elasmosaurus in ways that reflect a slightly different evolutionary path within the broader elasmosaurid family. Hydromosaurus, once considered a synonym of Elasmosaurus but now generally treated as a distinct genus, was present in the later Pierre Shale deposits and represents a somewhat different body proportion within the same general design. The ecological relationship between these long-necked species in the same seaway at the same time raises an interesting question. How did they avoid competing directly with each other? In modern marine ecosystems, closely related species that occupy very similar ecological roles tend to partition their habitat or their prey in subtle ways, using slightly different depths, slightly different prey sizes, or slightly different hunting grounds, so that their competition is reduced. The same logic presumably applied in the Cretaceous Seaway, but the fossil evidence for how it worked in practice is limited. Isotopic analysis of specimens from different species found in the same formation layers might eventually reveal that they occupied different parts of the water column, or different regions of the seaway's breadth, or different phases of the seasonal cycle. There is one particularly striking observation about the distribution of elasmosaurid species in the Western Interior Seaway that has not been adequately explained but that deserves attention. The Niobrara Formation, deposited in the middle phase of the seaway's existence, is dominated by elasmosaurid specimens from the Kansas portion of the formation, the deeper, more fully marine zone of the seaway. The Pierre Shale, deposited later in the seaway's history, in the northern and shallower phases of its existence, is also rich in elasmosaurid remains, but from different species and different proportional sizes. The shift in community composition between these two formations, deposited across a span of several million years, suggests that as the seaway's character changed, as it shallowed in the north and deepened in the south, as temperature and productivity patterns shifted, the elasmosaurid community that inhabited it shifted as well, tracking the changing conditions. Among the polycotylid short-necked plesiosaurs, Dolichohinchops osborni is the best-known Western Interior Seaway representative. It was considerably smaller than the large elasmosaurids. Most adults measured around 10 to 12 feet, which is 3 to 3.5 meters, and its anatomy tells a story of a different hunting strategy entirely. The long, relatively narrow snout was lined with sharply pointed teeth somewhat larger than the elasmosaurid's fish catchers, and the jaw proportions suggest an animal capable of seizing prey that was too large for an elasmosaur to handle comfortably. Whether Dolichops was migratory, in the way the large elasmosaurids apparently were, is unknown. Its smaller size would have made it capable of faster movement in terms of body length per second, and its different prey preference might have driven a different seasonal pattern. But its abundance in the same formations suggests it occupied the same seaway simultaneously, moving through the same water, if not along exactly the same seasonal corridors. There is something worth noting about the fossil record of these two groups, long-necked and short-necked, in the Western Interior Seaway that bears on the question of migration. The largest elasmosaurids appear more frequently in the northern formations, in the Bearpaw and Campanian Age Pierre Shale deposits of Alberta and Montana, than in the southern Niobrara formation of Kansas. The most spectacularly large elasmosaur specimens, animals that clearly represent old, fully mature individuals who had grown for decades, tend to come from the northern end of the corridor. This is consistent with the idea that the largest, oldest individuals spent more time in the north, in the summer feeding grounds where the greatest food resource was available, and may have been present there for longer periods than younger, smaller individuals whose energy requirements were lower and whose migration timing was perhaps less precisely calibrated. The discovery in 2011 of a small elasmosaur specimen from the middle of the Pierre Shale, described by researchers as juvenile based on its bone development and its size, added another dimension to the migration picture. A juvenile elasmosaur in the middle of the seaway, in rocks deposited roughly 76 million years ago, was not at either end of the migration corridor. It was somewhere in between, in what would have been open water over what is now South Dakota. Whether it was on its first southward migration following a northern summer, or on its first northward journey in the spring, or simply feeding in the middle section of the seaway in a way that did not involve the full length of the adult migration route, cannot be determined from the single specimen, but its presence establishes that young animals were in the water column of the open seaway, exposed to the same conditions and the same predators as the adults. Here is a fact about the Plesiosaur family tree that is worth carrying with you, because it adds a geographical dimension to the story that extends far beyond the Western Interior Seaway. Elasmosaurids were not confined to North America. They were a global group, found in marine deposits from Europe, from South America, from New Zealand, from Antarctica, from Japan. The same basic body plan, the very long neck, the small head, the 4 large paddle limbs, the barrel-shaped body, appeared on virtually every continent during the Cretaceous, in every ocean basin that was warm enough and productive enough to support them. The migration we have been following through the Western Interior Seaway was therefore a local expression of a behaviour that was, in some form, occurring in ocean systems around the world. New Zealand's Cretaceous marine deposits have been producing plesiosaur specimens for decades, and recent analysis of some of these specimens has suggested isotopic patterns consistent with seasonal movement through the ancient seas that once covered what is now the New Zealand region. Antarctic specimens, recovered from formations deposited in the shallow continental seas that covered parts of the Antarctic margin during the warm Cretaceous period, show growth ring patterns consistent with seasonal variation in conditions, the bone growing faster during productive periods and slower during less productive ones, in a pattern that might reflect a seasonal migration to more productive waters and back. The impression that forms from all of this is of a globally distributed family of reptiles that had, across millions of years of evolution, solved the problem of navigating seasonally variable oceans in a remarkably consistent way. By following the warmth, by moving between summer feeding grounds and winter resting grounds, by exploiting the seasonal gradient of productivity that characterized the warm Cretaceous seas as surely as it characterizes the modern ocean. The specifics varied by location, by species, by the particular geography of the ocean system each population inhabited. But the underlying strategy, follow the warmth, travel far enough to track the seasonal gradient, feed intensively in the summer grounds, rest in the winter grounds and travel again, was repeated in ocean after ocean around the globe. There is a word for the pattern we have just described. It is the word that biologists use to describe organisms that occupy a wide geographic range, but that achieve that range not by living everywhere simultaneously, but by moving seasonally through different parts of it. Cosmopolitan is the word most often used for wide-ranging species, but the more precise term for the behaviour is large-scale seasonal migration, and the organisms that practice it are among the most ecologically successful in every environment they occupy. Whales, sea turtles, many species of shark, nearly all of the world's great seabirds, all are long-distance seasonal migrants, and all of them are successful in the sense of numerically abundant and geographically widespread, in large part because their migrations track the seasonal pulse of productivity that makes the ocean, taken as a whole across all its seasons, far richer than any single part of it ever is at any given moment. The Elasmosaurids practiced this strategy for roughly 35 million years across the Cretaceous period, in seas spread across nearly every oceanic basin on the planet. They were extraordinarily successful, in the sense of being abundant, diverse, and persistent. They filled a specific role in the marine ecosystem with remarkable efficiency, and they did it through a combination of anatomical specialization and behavioral flexibility that allowed them to exploit the seasonal productivity of warm Cretaceous oceans in ways that no other large marine animal of their time exactly matched. The migration of the Western Interior Seaway was, in this light, not an unusual or exceptional behavior, but a local version of the characteristic behavior of a globally successful group. The thing Elasmosaurids were fundamentally for played out in one of the most productive marine environments the Cretaceous world contained. To follow the migration to its full extent, to truly feel the dimensions of the journey, requires an attempt to hold the seaway's geography in the mind as a coherent whole, rather than as a series of famous fossil formations associated with modern American states. The seaway was not Kansas. It was not Alberta. These are the names of the modern geography that sits on top of where the seaway once was, in the same way that Paris sits on top of a Roman town called Lutetia that has no obvious connection to the modern city above it. The seaway predates the mountains, the plains, the rivers, the soil itself. It is the original geography of the interior of the continent, and it does not map neatly onto anything that currently exists. Begin in the south, where the seaway connected to the open ocean. The connection point is approximately where the Gulf of Mexico now opens to the Atlantic, though the ancient geography was different enough that no modern map quite captures it. From this southern opening, the seaway extended northward through what is now Texas, Kansas, Nebraska, the Dakotas, Montana, and Saskatchewan, a distance of roughly 3,000 miles, which is about 4,800 kilometers. At its widest, this corridor was perhaps 900 miles across. At its narrowest, in the intervals when sea levels were slightly lower and the flanking landmasses pressed in from east and west, it may have been as little as 300 miles wide. The western edge of the seaway was defined for much of its history by the activity of the Sevier orogeny, the mountain-building event that was slowly pushing the western margin of the continent upward, creating the precursors of the Rocky Mountains and generating a vast blanket of sediment that eroded eastward into the seaway along its entire western length. This sediment influx from the west was one of the factors controlling the seaway's depth and width in the western portion of the corridor. Where sediment deposition was rapid, the seaway shallowed and narrowed, and the shoreline migrated eastward. Where deposition slowed, the water deepened again, and the shoreline retreated west. The eastern edge of the seaway was bordered by a fundamentally different kind of landscape. The eastern flank of the continental interior, the Appalachian region, and the broad lowlands stretching westward from it, was geologically ancient and tectonically stable, a cratonic platform that had been tectonically quiet for hundreds of millions of years. The shoreline on this eastern side was lower, more gradual, and more stable than the western shoreline, producing an extensive coastal plain of subtropical forest and wetland that graded imperceptibly into the shallow coastal waters of the eastern seaway margin. What would you have seen from the surface of the seaway, looking east, in the peak period of its existence? A low horizon of coastal forest, the edge of the land barely distinguishable from the water, except by the darkness of the vegetation against the lighter sky. The transition from open water to shoreline was not a dramatic change of scenery in most places. It was a gradual shallowing, a change in the bottom visible through the increasingly clear water, a shift from open sea to coastal lagoon to swamp to forest, without a clear boundary anywhere along the gradient. This gradual transition was important for the ecology of the seaway's margins. It created an enormous extent of shallow, productive coastal habitat where terrestrial and marine ecosystems overlapped, and where the animals of both worlds occasionally encountered each other. Hadrosaurs, the duck-billed dinosaurs, were among the most abundant large animals in the coastal forests and wetlands of the seaway's eastern margin. Their remains are found in the same geological layers as marine fauna, sometimes in deposits that represent coastal environments where both terrestrial and marine organisms were buried together. Some paleontologists have proposed that hadrosaurs were capable of swimming across arms of the seaway, a proposition that is supported by the broad, paddle-like structure of hadrosaur hands and the hydrodynamic characteristics of their body form as modelled by researchers using fluid dynamics software. Whether this swimming ability was used to cross significant stretches of open water or merely to navigate coastal marshes and flooded forests is not clear. The northern end of the seaway's corridor is perhaps the most geographically unfamiliar to modern eyes, because the modern geography of the Canadian North has been so thoroughly reshaped by the glacial events of the past 2 million years that the Cretaceous landscape beneath it is almost inaccessible to the imagination. The seaway in the north opened into what paleontologists call the Boreal Sea, the warm Arctic Ocean of the Cretaceous, which connected through the opening at the top of the seaway to the broad, warm basin of the Pacific to the west and to the developing Atlantic Ocean to the east. The connection was not always open. Tectonic activity and changing sea levels caused the seaway's Arctic end to close and reopen repeatedly across its history. But during the peak periods of Elasmosaur migration, the northern end of the corridor was open to the broader Arctic Ocean, providing a connection to a much larger marine system. This northern connection has an implication for the Elasmosaur migration that is rarely discussed. An Elasmosaur travelling north through the seaway did not have to turn around at some arbitrary northern boundary and reverse course. It could, in principle, exit the seaway entirely through the northern opening and enter the broader Arctic Ocean, feeding in the offshore waters there before eventually re-entering the seaway through the same northern opening for the return journey south. Whether any individuals did this, and how frequently, is unknown from the current fossil evidence. But the geography permitted it, and an animal following a temperature gradient rather than a fixed route would have followed the warmest available water wherever that led. The shallowness of the seaway deserves emphasis here, because it is one of the features most difficult to reconcile with the image of an open sea. In its deepest portions, the central Kansas section of the Niobrara Formation records these depths most clearly. The seaway reached roughly 600 metres, or about 2,000 feet. This is not shallow by the standards of most freshwater bodies, but it is extremely shallow by the standards of a modern ocean, where depths of 2,000 to 4,000 metres are common even in continental shelf areas. The shallow depth meant that the seaway was fully illuminated to the bottom across wide areas of its extent, that temperature fluctuations at the surface penetrated to the seafloor in the shallower regions, and that the animals of the water column and the animals of the seafloor were in closer contact with each other than they would be in a deep ocean. For the Elasmosaur, the shallowness had a particular implication. There was no deep water refuge. In a deep ocean, an air-breathing marine animal threatened by a surface predator has the option of diving deep, to a depth where pressure and cold and darkness deter most pursuit. In the seaway, the bottom was reachable. A diving Elasmosaur fleeing a surface threat would have hit the seafloor long before reaching any depth that offered the darkness and cold that deep water refuges provide in modern oceans. The seaway was, in this sense, fully exposed from surface to bottom, and there was nowhere within it that was beyond the reach of something determined to follow. This fact illuminates another dimension of the migration's risk. The entire 10,000-mile corridor was, from a predator avoidance perspective, a shallow, well-lit, fully accessible environment with no refugia beyond the surface and the seafloor, neither of which offered any real protection from animals adapted to hunt in the water column. The Elasmosaur's strategy in this environment was not to hide, but to be too large and too capable of evasion to make attacking it worthwhile for most potential threats. Size was the refuge, and the migration route through shallow water was the cost of pursuing the seasonal productivity that the migration was designed to exploit. Here is a detail about the seaway's geography that connects back to the question of the migration's navigational cues. The seaway did not have uniform currents across its length. Its narrowness, combined with the wind patterns typical of mid-latitude Cretaceous North America, would have created a consistent pattern of current flow, northward along one side and southward along the other, in the same general pattern, that narrow water bodies and coastal currents produce today. An Elasmosaur that learned to use these currents, to position itself in the northward flowing current during the spring migration and the southward flowing current during the autumn return, would have reduced its energy expenditure significantly, covering the same distance with less muscular effort than an animal swimming against or across the prevailing flow. Modern long-distance migrants routinely use ocean currents in exactly this way. Sea turtles making transoceanic migrations position themselves in specific current systems that carry them in the right direction, reducing their own swimming effort. Whales follow the boundaries between water masses of different temperatures, which are often associated with current boundaries, and use the energy of the current to supplement their own swimming. The evidence that elasmosaurs did the same thing is not direct. No current use behavior can be read from a fossil, but the anatomy of the animal, built for sustained low-energy travel rather than high-speed swimming, is precisely what you would expect from an animal that relied on external forces to supplement its own locomotion. The Seaway, taken as a whole, from its tropical southern connection to its Arctic northern opening, from its eastern forest margin to its western mountain-building shoreline, from its surface to its illuminated chalk bottom, was a complete and coherent world, an animal that spent its entire life within it, migrating its full length twice a year and filling the intervals with the steady, unhurried work of feeding and travelling, would have known every part of it. Not consciously, not with any cognitive representation of geography that we would recognise as knowledge, but in the way that all living things know the world they have always been part of, through the body, through the accumulated experience of the physical environment as it was actually encountered, 1 degree of temperature and 1 school of fish, and 1 smooth-stoned northern riverbed at a time. The Western Interior Seaway did not end abruptly. Nothing of geological scale does. Its end was the accumulation of small shifts across millions of years, each one too gradual to notice across any individual lifetime, each one adding its small quantity to a total that eventually crossed a threshold from which there was no return. It was the consequence of forces that had nothing to do with the biology of the animals living in it, forces operating in the solid earth itself, in the movement of tectonic plates and the slow uplift of mountain ranges that were, for the animals of the Seaway, simply the distant western horizon. The process that ended the Seaway was the same process that created the Rocky Mountains, a collision between tectonic plates at the western margin of North America that pushed the western edge of the continent upward, while simultaneously depressing the interior immediately to the east of the rising range. This depression created the deep basin that, in the Seaway's peak period, held the deepest and most fully marine water in the central corridor. But as the mountains rose higher and the collision intensified, the nature of the depression changed. Instead of creating a basin that the sea could fill, the rising range created a shallow, wedge-shaped ramp of sediment that eroded eastward from the mountains and began filling the western edge of the Seaway from the inside. The filling was slow, but it was consistent. River systems draining the rising mountains carried an enormous sediment load eastward into the Seaway, depositing their burden in deltas and floodplains that extended progressively eastward into what had been open water. The western margin of the Seaway was becoming land, not through any dramatic event but through the quiet, patient accumulation of sediment that rivers always deposit when they reach standing water, and their carrying capacity exceeds the water's ability to transport the material further. At the same time, global sea levels were declining slightly as the climate of the very late Cretaceous began a gradual cooling from its peak warmth. The extremely high sea levels of the Middle Cretaceous, the levels that had made the flooding of the continental interior possible in the first place, were a product of the exceptional warmth of that period, which kept water in liquid form in the polar regions rather than locking it in ice. As temperatures began to decline toward the end of the Cretaceous, even the modest cooling was sufficient to allow some sequestration of water in the beginnings of polar ice formation, which drew water from the ocean and lowered global sea levels by small but meaningful amounts. The combination of sediment infilling from the west and declining global sea levels from below created a seaway that was gradually shallowing, narrowing, and retreating at both ends simultaneously. The deep central basin began to fill, the shallow northern extension began to drain. The southern connection to the open ocean, always the most geometrically complex part of the seaway's geography, began to shift and change character as the water level dropped. What had been open marine conditions progressively became lagoonal conditions, then estuarine conditions, then freshwater, and eventually terrestrial. The elasmosaurs that were alive during this period of gradual seaway retreat were living through a slow degradation of their habitat that they could not have been aware of across any individual lifetime. A change of a few miles in the extent of the seaway, or a cooling of a degree or two in the northern waters, or a slight reduction in the productivity of the summer bloom. These were the kinds of changes that a single animal would have experienced as ordinary year-to-year variation rather than as a trend. Only across many generations would the cumulative effect have become apparent in a biological sense, as the population that depended on the full-length migration corridor found that the northern end of the corridor was shrinking and the productivity it had depended on was diminishing. This gradual habitat reduction is thought to have been one of the factors contributing to the decline of elasmosaurid diversity and abundance toward the very end of the Cretaceous, before the asteroid impact that ended everything. By the Maastrichtian stage of the late Cretaceous, the final few million years before the end Cretaceous extinction, the number of elasmosaurid species in the Western Interior Seaway appears to have been declining relative to earlier periods. The formations deposited in the last few million years of the seaway's existence contain fewer elasmosaur specimens than the earlier Niobrara and Pierre Shale formations, and the specimens that do occur tend to be concentrated in the deeper, more fully marine portions of the still existing seaway, rather than distributed across the full breadth and length of the earlier, more expansive system. Whether this decline in recorded abundance reflects a genuine decline in population, or simply a reduction in the extent of the depositional environment that preserved the fossils, a smaller seaway produces less seafloor sediment in which to preserve animals, is a question that cannot be resolved with current evidence. But the pattern is consistent across multiple studies of the late Cretaceous fossil record, and it suggests that the elasmosaurids were under environmental pressure in the final phases of the seaway's existence, even before the asteroid arrived. The asteroid impact of 66 million years ago ended everything simultaneously, and without regard for which animals were already struggling and which were thriving. From the perspective of an elasmosaur in the diminished but still functional seaway of the Maastrichtian, the last normal day would have been exactly like the previous 10,000 last normal days, the water warm enough, the fish present, the paddles working in their steady rhythm, the chemical gradient of the water telling the body it was in the right part of the corridor for the time of year. And then, not suddenly in any way that the animal would have experienced as sudden, the light that the whole system depended on began to diminish, and the phytoplankton that needed the light began to fail, and the food web that rested on the phytoplankton began to collapse from the bottom upward. The elasmosaurs did not go extinct because something ate them. They did not go extinct because the mosasaurs finally outcompeted them. They did not go extinct because the seaway drained away and left them stranded. They went extinct because the thing that everything in the ocean ultimately depends on, sunlight, and the photosynthesis that sunlight enables, was disrupted on a global scale for long enough to collapse the food webs that sustained them. The largest animals need the most food, and when the base of the food web fails, the largest animals starve first. What the last elasmosaurs experienced in the months after the impact is not something that the fossil record can reveal with any specificity. The bones of the last individuals are indistinguishable from the bones of their predecessors. There is no physical mark of the ending, no scar in the bone that records the moment when the food simply stopped coming. There is only the boundary layer in the rock, the thin band of iridium-enriched sediment deposited globally by the fallout from the asteroid impact, above which no more elasmosaur bones appear, and below which the record of a very long dynasty comes to its close. The seaway itself continued for a time after the extinction, emptied now of the large reptiles that had filled it. It continued shallowing, continuing its long retreat from the continental interior. By roughly 66 to 60 million years ago, the seaway had separated into a northern and southern component, with dry land across the middle. The southern component drained away first, leaving a vast flat plain of former seafloor that would eventually become the agricultural heartland of North America. The northern component persisted somewhat longer before it too retreated to the margins and eventually became the shallow coastal waters of what is now the Hudson Bay region, a remnant of the great inland sea, cold now and much smaller and empty of everything that once made the original sea remarkable. The land that remains where the seaway once was does not look like former seafloor. It looks like farmland, like prairie, like the flat rolling landscape of the Great Plains that most people drive across quickly on interstate highways thinking of somewhere else they are going. The chalk and shale that were the seaway's floor lie beneath the topsoil, accessible in road cuts and eroding bluffs, and the weathered exposures of seasonal stream banks. The bones of the animals that lived in the seaway emerge from these exposures every spring, released by frost and rain, and the patient work of erosion that has been going on since the land reasserted itself 66 million years ago. They are still coming out of the ground. They always will be, as long as the stone that holds them continues to erode. There is a quality of light in the late afternoon in Kansas that is particular to that landscape, and it is the light that falls on the chalk bluffs of the Niobrara Formation when the sun is low and the sky is clear. The chalk is white, almost startlingly white against the brown grass and the blue sky, and the light at that hour gives it a warmth that makes it look almost like stone that has been inside a building for a long time, kept from the weather. These bluffs, which rise from the floors of river valleys that have cut down through the ancient sediment to expose the chalk below, are the walls of the seaway made visible. They are the compressed, mineralized remains of billions of tiny marine organisms that fell to the bottom of the Western Interior Seaway across millions of years and were buried and compressed and eventually turned into something as close to permanent as sedimentary rock ever gets. The history of paleontological discovery in the Niobrara chalk reads like a story from a different era of science, because it is. The first major expeditions to the Kansas chalk bluffs took place in the 1860s and 1870s, during the period that has come to be called the Bone Wars, the bitterly competitive race between paleontologists Othniel Charles Marsh of Yale and Edward Drinkercope of Philadelphia to describe and name as many new prehistoric species as possible in as short a time as possible, at any cost to either scientific rigor or personal dignity. Both men sent teams to the Kansas chalk, and both teams found remarkable things. The material coming out of the chalk in those early years was startling enough to cause serious disruption to scientific thinking about the history of life. Mosasaurs in extraordinary numbers and completeness, fish of unprecedented size, a toothed bird, Hesperornis, that swam underwater using its feet and demonstrates that birds in the Cretaceous had not yet lost all traces of their theropod dinosaur ancestry, and plesiosaurs, including the specimen of Elasmosaurus platurus that would become one of the most famous fossils in American paleontological history, if only because of the mistake made in its initial reconstruction. The story of the Elasmosaurus reconstruction era is well known in paleontological circles, but worth retelling here, because it illuminates something important about the process by which we come to understand extinct animals. The specimen was collected in 1867 by a physician and amateur fossil collector named Theophilus Turner, who sent it to Edward Drinkercope in Philadelphia. Cope, working with the fragmentary remains of an animal unlike anything he had previously seen, assembled a reconstruction in which the head was placed on the wrong end, attached to what was actually the tail, rather than to the tip of the very long neck. The error was pointed out by Othniel Charles Marsh, Cope's rival, in a correspondence that is remembered as one of the more pointed exchanges in the history of natural history. The correction required acknowledging that the neck was, in fact, longer than the tail, that the head went on the short end and the tail on the long end rather than the reverse. This seems obvious in retrospect, but it was not obvious to anyone encountering the anatomy for the first time. Nothing in the familiar catalogue of living animals prepares the observer for an animal whose neck is longer than its body, and the human tendency is to assign the familiar proportions. Head at one end, tail at the other, neck approximately proportional to both, to any unfamiliar skeleton. The Elasmosaur defeated this tendency entirely. The subsequent history of Niobrara research is one of steady accumulation rather than dramatic revelation. Season after season, generation after generation of researchers has returned to the chalk bluffs of western Kansas and the related formations of Nebraska, the Dakotas, and Canada, extracting specimens from rock that requires patience and care proportional to the patience and care that went into their burial 80 million years ago. The tools have improved enormously. The delicate air scribes and dental picks that replace the rock around a bone grain by grain, the consolidants that stabilize fragile material before it leaves the matrix, the micro-CT scanners that allow researchers to see inside bones without destroying them, but the basic work remains what it has always been, sitting in the chalk, in the wind and the sun, asking the stone to give up what it has been keeping. What has been learned from this accumulated effort is remarkable in its detail, and in the picture it builds of a world that left no survivors. The diet of the Niobrara mosasaurs is known from preserved stomach contents. The diving behaviour of Hesperornis is known from bone density measurements that reveal a degree of osteosclerosis, the thickening and densification of bone that is common in diving birds, consistent with deep, sustained dives. The reproductive biology of the seaway's elasmosaurids is known from the South Dakota specimen with its preserved embryo. The growth rates of multiple species are known from bone histology. The water temperature of the seaway at different times and in different parts of its extent is known from foraminiferal isotope records. The seaway is, in the language of paleontology, well resolved, meaning that the fossil record is dense enough to support detailed ecological reconstruction, rather than the sparse fragmentary record that characterizes most of the history of life in most places. But there is something that the chalk remembers beyond what any individual specimen records, and it is worth sitting with for a moment before we continue. The chalk itself, the rock, not the fossils within it, is a physical record of the biological productivity of the seaway. Every cubic centimetre of Niobrara chalk represents the compressed remains of organisms that lived and died and sank to the bottom across a specific interval of time. The thickness of the chalk, the rate at which it accumulated, the variation in its texture and composition across different layers, all of these are records of the changing productivity and character of the seaway's water through time, readable by people who know how to ask the right questions of the right instruments. The Niobrara Formation is roughly 70 to 200 feet thick across its extent in Kansas, depending on location and the completeness of preservation. This thickness represents roughly 4 to 5 million years of accumulation in the deepest, most complete sections. 4 to 5 million years of biological productivity, compressed into a thickness that a person could climb in a few minutes. Every foot of that chalk represents roughly 25,000 years of the seaway's existence. Every inch represents roughly 2,000 years. The thin layer of chalk that might adhere to the sole of a boot after a walk across a chalk bluff represents, in all likelihood, more time than all of recorded human history. This is the kind of mathematics that the chalk performs on the human sense of time, and it is worth performing it consciously, because it is the context in which the Elasmosaur migration took place, and in which the fossil evidence that reveals it was preserved. The animal we have been following made its 10,000-mile migration, back and forth through the length of the seaway, across a span of perhaps 60 or 70 years. In the chalk record, that lifetime represents a fraction of a millimetre of accumulated sediment. The whole history of the Elasmosaurid family in the Western Interior Seaway, every migration of every individual across several million years, is contained within a formation that a person could examine in an afternoon. Here is a lesser-known fact about the Niobrara Formation that connects directly to the question of what happened to the animals that lived in it. The chalk does not end gradually, it ends abruptly. At the top of the Niobrara, the transition to the overlying Pierre Shale, the formation deposited in the later, shallower, more terrestrially influenced phase of the seaway, records a significant environmental change in the character of the sediment and in the composition of the fossil community. Some species that are abundant in the Niobrara are absent or very rare in the Pierre. Others appear in the Pierre that were not present in the Niobrara. The community changed as the seaway's character changed, and the boundary between the two formations is a boundary between two phases of the same sea's history. Above the Pierre Shale, the formations become increasingly terrestrial. River deposits, floodplain sediments, the debris of a landscape that is no longer a sea, but is becoming the continental interior. Somewhere in those terrestrial formations, the end Cretaceous extinction boundary appears, marked by the thin iridium layer that signals the global fallout from the asteroid impact. Above that boundary, everything is different. The marine formations resume at some distance, the later smaller seas that occupied the margins of the continent. But they are different seas, populated by different animals, belonging to an entirely different chapter of Earth's history. The chalk is therefore a closed book. It records a specific interval of time, in a specific body of water, with a specific community of organisms, and then it stops. The book ends not with a gradual trailing off, but with the environmental transition from deep chalk sea to shallower shale sea to terrestrial landscape to the extinction boundary above. Everything the chalk has to say about the migration of the elasmosaurs is contained within its pages. No later formation extends the story. No younger formation adds another chapter. The chalk is what there is, and what there is, it turns out, is quite a lot. Enough to reconstruct the migration in its essential outlines, enough to follow the animal through its seasonal circuit, enough to sit here in the warm stillness of wherever you are now and understand what it was to be a long-necked traveller in a sea that is gone. The Western Interior Seaway is gone, the elasmosaurs are gone, the whole community of animals that shared those warm, shallow waters with them. The mosasaurs, the giant sharks, the enormous fish, the toothed birds and the soaring pterosaurs, all of them are gone, replaced first by nothing, and then, across tens of millions of years of recovery, by a marine community that has no direct lineage connection to the one that came before. The ocean rebuilt itself, as it has always rebuilt itself, using whatever survived and whatever those survivors gave rise to. The result is the ocean we have today, beautiful and complex and full of life, and bearing almost no resemblance to the ecosystem that preceded it. And yet, there are animals in the modern ocean whose behaviour echoes the elasmosaur migration with an exactness that is either coincidence or convergence, the phenomenon by which different evolutionary lineages, shaped by similar environmental pressures, arrive at similar solutions to the same biological problem. The convergence, in this case, is the behaviour of following warm water through a seasonally variable ocean corridor across very large distances, twice a year for most of an animal's adult life. The grey whale is perhaps the closest behavioural analogue. Grey whales make an annual migration between summer feeding grounds in the Bering and Chukchi seas of the Arctic and winter breeding and calving grounds in the warm lagoons of Baja California, Mexico. The one-way distance is roughly 6,000 miles, which is about 10,000 kilometres, comparable in scale to the estimated length of the elasmosaur migration. The timing is driven by the same basic logic. The Arctic summer provides extraordinary feeding opportunities under the influence of the midnight sun and the great seasonal bloom of Arctic productivity. The warm southern lagoons provide the thermal conditions favourable for breeding and calving. The animals travel at an average speed of about 3 to 5 miles per hour, almost exactly the estimated speed of an elasmosaur, and the journey takes roughly 2 to 3 months. The differences between a grey whale and an elasmosaur are of course enormous. The grey whale is a mammal, warm-blooded in the full endothermic sense, breathing air through a nasal passage designed for rapid surface respiration, feeding on amphipods scooped from the seafloor rather than fish plucked from mid-water schools. It is a social animal that migrates in groups, communicating with its companions across significant distances using acoustic signals that travel efficiently through the water column. The elasmosaur was a reptile whose thermoregulatory status remains uncertain, feeding with a long neck and interlocking fish-catching teeth, apparently solitary in its migrations based on the isolated nature of most fossil specimens. But the behaviour, the annual north-south transit through a temperature gradient, the summer feeding in high-productivity waters, the winter resting in warm low-latitude seas, the sustained long-distance travel at walking pace. This behaviour is so similar between the two animals that it represents one of the clearest examples of convergent evolution in the history of large vertebrate biology. Two completely different lineages, separated by 66 million years and descended from entirely different ancestors, arrived at the same seasonal behavioural strategy, because the ocean, despite having changed its inhabitants completely, has not changed the underlying physics that make long-distance seasonal migration the most efficient way for a large air-breathing animal to exploit the seasonal variation in marine productivity. The leatherback sea turtle offers a different but equally instructive parallel. Leatherbacks are the largest living turtle, reaching up to 6 feet in length and weighing up to 1,500 pounds, considerably smaller than an elasmosaur, but large enough to warrant the comparison. They are the most migratory of the sea turtles, making transoceanic journeys of up to 10,000 miles between their nesting beaches in tropical regions and their summer feeding grounds in cold water areas rich in jellyfish. They navigate these journeys apparently using geomagnetic sensing combined with water temperature detection, following the boundaries of ocean current systems and temperature fronts that mark the edges of productive zones. The leatherback's diet is almost entirely jellyfish, soft-bodied prey that requires no hard crushing teeth, just a large flexible mouth and a throat lined with backward-pointing spines that prevent ingested prey from escaping. This is different enough from the fish hunting of elasmosaurs that the dietary parallel is not useful, but the navigational and locomotory parallel is striking. Leatherbacks cruise at approximately 2 to 3 miles per hour during their open ocean transits, again almost exactly the estimated speed of the migrating elasmosaur, and they maintain that speed day and night without stopping to sleep in the way that a land animal would, sustaining the slow, consistent forward progress that long-distance migration requires. Here is something about the leatherback that bears directly on a question raised earlier about elasmosaurid thermoregulation. Leatherback sea turtles maintain a body temperature significantly above the surrounding water temperature, even when swimming in cold water. They do this not through endothermy, not through internal heat generation the way mammals and birds generate heat, but through a combination of countercurrent heat exchange systems in their blood vessels and the simple thermal mass of a very large body, which loses heat slowly enough that even modest metabolic activity maintains a body temperature several degrees warmer than the ambient water. Researchers call this gigantothermy, the ability of very large animals to maintain stable internal temperatures simply by virtue of their size, regardless of the specific mechanism of heat generation. Elasmosaurs at their largest were considerably bigger than leatherback sea turtles. If gigantothermy was available to the leatherback at 1,500 pounds, it was almost certainly available to an elasmosaur at several tons. This would have allowed the elasmosaur to maintain a relatively stable body temperature across the full range of water temperatures encountered during the migration, from the warmest southern waters to the cooler northern summer waters, without requiring the full suite of physiological adaptations that true endothermic animals have evolved for cold water tolerance. The large body was, in effect, its own insulation, carrying the warmth of the southern waters northward in the thermal mass of its own flesh, and releasing it slowly over the weeks of the northern residents. The sperm whale provides a third point of comparison, and in some ways the most instructive. Sperm whales are the largest toothed predators alive today. Large males can reach 60 feet in length, which is approximately the length of the largest elasmosaurs. They dive to depths of several thousand feet in pursuit of deep-water squid, spending most of their lives in the deep ocean far from any coastline. They are long-distance travellers, but not in the same seasonally regular north-south sense as grey whales. Their movements are more complex and less predictable, following the distribution of their prey across a three-dimensional ocean environment that has no simple seasonal gradient comparable to the Arctic to temperate gradient that drives grey whale migration. What the sperm whale comparison illuminates about the elasmosaur is not the behaviour but the scale. The sperm whale demonstrates that very large, air-breathing, diving predators can persist in the modern ocean and can reach body sizes comparable to the largest Cretaceous marine reptiles. The pathway to that size, in the sperm whale's case more than 50 million years of whale evolution following the ancestral land mammal's entry into the sea, was longer and more complex than the elasmosaur's evolutionary history. But the destination was similar, a very large animal, travelling long distances through open ocean, using a combination of its size and its efficiency of locomotion to sustain a way of life that smaller animals could not maintain. The ocean current systems of the modern world bear one more comparison to the Western Interior Seaway that is worth making explicit. The Gulf Stream, which flows northward along the eastern seaboard of North America and across the North Atlantic, carries warm tropical water into high latitudes in a way that supports marine productivity patterns not entirely unlike the seasonal productivity gradient that the Western Interior Seaway exhibited. The northern extension of the Gulf Stream's influence, the warm North Atlantic drift that moderates the climate of Western Europe, creates a zone of enhanced marine productivity along its boundaries, and it is along these boundaries that many of the modern ocean's long-distance migrants are found. Whales, sea turtles, large pelagic sharks, and migratory fish that follow the warm current north in summer and south in winter. The elasmosaur migration through the Western Interior Seaway was, in this light, not a peculiarity of the Cretaceous world, but an expression of a recurring pattern in the history of marine life, the tendency of productive seasonal oceans to support long-distance migration in their largest inhabitants. Every time an ocean system has developed a strong seasonal productivity gradient across a large geographic area, large air-breathing animals have evolved to exploit it by moving with the gradient across its full length. Ichthyosaurs likely did it in the Triassic and Jurassic oceans. Elasmosaurs did it in the Cretaceous. Mosasaurs may have done a version of it, though the evidence is less developed. And today, in the ocean that replaced them all, the grey whales and leatherbacks and sperm whales do something comparable, following the same physics through a different ocean with different animals, arriving at the same broad conclusion: that the warmth always comes, and where the warmth goes, the life follows. There is an Elasmosaur vertebra in a museum drawer in Lawrence, Kansas. It is not on display. It is a study specimen, one of many hundreds of bones recovered from the Niobrara Formation over the past century and a half of collecting, stored in the standard manner of natural history museum collections, in acid-free tissue paper, inside a shallow tray, inside a numbered cabinet, in a climate-controlled room that smells faintly of old stone and the particular dry chemical smell of the consolidants used to stabilize fragile fossil material. The bone is roughly the size and general shape of a hockey puck, though somewhat thicker, with a slightly convex articular face on each end where it would have contacted the adjacent vertebrae in the living animal. If you were to hold this vertebra and look at it carefully, you would see, on one of its lateral faces, a small area of irregular texture that is different from the smooth surface everywhere else. The texture is raised slightly rougher, slightly more porous than the surrounding bone. A paleontologist who examines this area under magnification would identify it as healed bone, the material deposited by the animal's own biological repair process in response to an injury that occurred during the animal's lifetime. The injury was not fatal. The animal lived long enough for the repair to be essentially complete. And then eventually it died of something else, and its bones settled into the chalk, and the chalk accumulated above them, and the sea retreated, and the prairie grew, and the Pleistocene ice came and went, and the settlers arrived, and the town of Lawrence was founded, and the university was built, and one autumn a student on a class trip to a road cut found the bone exposed in the chalk and brought it back. That healed injury is one data point. It establishes that this particular individual experienced a non-fatal trauma to this particular vertebra at some point in its life. It does not tell you what caused the trauma. It does not tell you how old the animal was when it happened or how long after the injury the animal lived. But it is a real piece of information, derived from a real bone that came from a real animal that lived a real life in a real sea 80 million years ago. And it is more information than we had before someone picked it up and brought it back to a laboratory. Multiply this by the thousands of specimens in collections across North America, and by the dozens of published studies that have analysed those specimens using every technique available, from simple morphological comparison to the most recent mass spectrometric methods, and the picture that builds up is not a complete picture. It will never be a complete picture, but it is a remarkably detailed one for something that vanished 66 million years ago. The migration we have been following through these hours of darkness is not fiction. It is an inference, carefully drawn from multiple lines of physical evidence, tested against what is known about the biology of analogous modern animals, and held with the appropriate confidence of something that is very likely true without being absolutely certain. Here is what we can say with reasonable confidence, drawn from the evidence as it stands. Elasmosaurids were abundant in the Western Interior Seaway across several million years of the late Cretaceous. They were large animals, the largest individuals reaching 40 to 46 feet in length, with necks accounting for more than half of that length. They gave birth to live young in open water. They swallowed stones that served some combination of digestive and possibly buoyancy functions. They fed primarily on fish and soft-bodied cephalopods, captured with a precision jaw mechanism optimized for accuracy rather than force. Isotopic signatures in their fossilized teeth and bones record water chemistry variations consistent with movement between different parts of the seaway across individual lifetimes. The pattern of variation in those signatures is consistent with seasonal, north-south migration across the full length of the seaway. Here is what we can say with somewhat less confidence but with good supporting evidence. The migration covered a distance comparable to modern grey whale and leatherback turtle migrations, on the order of 5,000 miles each way or 10,000 miles per year. The motivation for the migration was the seasonal productivity gradient in the seaway, with summer feeding grounds in the north and winter resting grounds in the south. The timing of the northward and southward movements was controlled by water temperature cues and possibly by photoperiodic cues from changing light levels. The animals may have shown site fidelity, returning to the same general areas in successive years, based on the consistency of isotopic signatures across multiple growth periods in individual specimens. And here is what remains genuinely unknown, where the evidence runs out and honest science acknowledges the boundary. Whether the migration was undertaken by all individuals of all ages, or only by fully adult animals, or by separate age classes following slightly different routes. Whether it was a solitary migration, or whether animals travelled in loose associations that provided some social benefit. Whether there were specific calving grounds at either end of the migration, or whether birth occurred opportunistically throughout the corridor. Whether the animals had any form of acoustic communication during migration. Whether they used geomagnetic sensing, temperature gradients, chemical cues, or visual landmarks for navigation, and in what proportion. These questions will be answered, if they are answered, by future specimens analysed with future techniques, by researchers who have not yet been born working on problems that have not yet been properly framed. The history of paleontology is largely the history of questions that seemed unanswerable, becoming answerable through the development of new analytical tools. The question of whether elasmosaurs migrated would have seemed completely unanswerable 50 years ago. There was no technique available that could extract the geographic information from fossil bone. Today, the technique exists and has been applied. The results are suggestive rather than conclusive. In another 50 years, the technique will likely have been refined to the point where the migration can be reconstructed in considerably more detail, and the questions that currently sit at the edge of the evidence will have moved either into the answered column or into the more clearly unanswerable column. The patience required for this kind of scientific progress is, in its own way, a form of the same patience that the migration itself required. Not the patience of an individual animal crossing a 1,000-mile corridor, but the patience of a research program extending across generations of scientists, each adding one small layer of understanding to a record that holds its full meaning in reserve until the tools become sophisticated enough to extract it. The elasmosaur waited in the chalk for 80 million years. The question of where it went waited in the elasmosaur's teeth for another century or two after the first bones were collected. The answer is still coming, layer by layer, specimen by specimen, year by year. Here is a final unknown fact to carry with you into the night, one that few people outside the community of plesiosaur researchers know. Elasmosaur specimens have been recovered from every continent on Earth, including Antarctica. The Antarctic specimens, recovered from rocks deposited in the shallow seas that covered the margins of the Antarctic continent during the warm Cretaceous, include animals that were apparently living and dying in waters at what are now some of the coldest latitudes on Earth, though the waters were warm then, perhaps 15 to 20 degrees Celsius, subtropical by any standard. These animals were making their own migrations, following their own seasonal gradients, in a world where the geography of the ocean and the location of the continents was different enough from today that the very concept of Antarctica as a place of ice and cold would have been incomprehensible. A plesiosaur in Antarctic waters 80 million years ago was not in a cold place. It was in a warm, productive, well-lit sea in the high southern latitudes, as ordinary a marine environment for its time as any in the Western Interior Seaway. The fact that the geography beneath those waters has since moved to the pole and been covered by ice does not change what it was then. The past does not revise itself to match the present. What was warm remains warm in the record of the rocks, and what swam there remains present in the stone, waiting in the patient way that stone has always waited for someone to come and look. That waiting is almost over for tonight. The story has been told as completely as the current evidence allows. The long-necked traveller has made its full annual circuit, 10,000 miles from the warm south to the abundant north and back again, carrying its smooth stones in its belly and its isotopic record in its teeth, leaving its bones in the chalk for the curiosity of a species that would not exist for another 80 million years. It did this quietly, unhurriedly, without drama, the way all the most persistent things in nature are done. And then the light failed at the end of the Cretaceous, and it was gone, but not before the chalk had recorded it, not before the teeth had preserved the signature of every sea it swam through, not before the bones had healed over their injuries and continued moving, continued following the warmth, continued doing the thing they were built to do, right up until the doing of it was no longer possible. Thank you so much for watching. If you would like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one. And now, let the story settle. Let the chalk bluffs and the warm shallow sea and the long neck rising in the evening light all settle into the comfortable distance of something that happened a very long time ago, safely and completely, in a world that the present world has forgotten how to visit except through careful inquiry and patient stone. The sea is there, if you want it. It is always there, in the dark, quiet behind closed eyes, warm and shallow and impossibly wide, stretching from horizon to horizon, under a sky that has a different quality than the sky you know. A little warmer, a little more golden. The sun at a slightly different angle, the light falling on water that is not quite the colour of any modern sea. You do not have to do anything. You do not have to follow anything or understand anything or arrive anywhere. The migration is complete. The animal has made its circuit. It is resting now, somewhere in the warm southern water, the long neck drifting in the mild current below the surface, the small head still, the breath coming slowly and evenly in the way that breath comes when there is nothing required of you and nowhere particular to be. The water is warm, the light is almost gone, the last of it lying flat and golden across the surface of the sea before it fades into the particular blue that comes just before dark. The chalk on the bottom is pale and quiet and perfectly still. Everything that needs to have happened has happened. Everything that needed to travel has travelled. The year has completed its circuit and the season has turned, and the warmth will return when it returns, as it always has, as it always does. You are here in the warmth too. Your own breath is slowing. The day you came from has already become something smaller, further behind you than it was a moment ago. The story has carried you somewhere gentle, somewhere the pace of things matches the pace of breathing in the last moments before sleep. Let the warm water carry you the rest of the way. There is nothing left to hold on to. The long-necked traveller has completed its 10,000 miles season after season, year after year, carrying its smooth stones and its isotopic record and its patient body through the warm corridor of a vanished sea. It did not hurry. It did not worry. It simply moved, steadily and with great reliability, in the direction that the warmth indicated, and trusted that the warmth would be there, and it always was. The warmth is here too. Your eyes are closed, or nearly closed, and the weight of the day is becoming the weight of sleep, which is gentler, and the water is very warm and the chalk is very pale and still, and somewhere below you the long shape is drifting in the last of the light, and the light is almost gone now and the water is holding everything, and there is nothing more to know tonight, and nothing more to carry, and the sea is very warm, and you are very still, and it is time to sleep. If you like this video, let me know where in the world you're watching from and what time it is. I'm always curious about that. And if you have a topic you would like to see explored, leave it in the comments below. Sleep well.